Okay, so I think we can start now. What we're going to talk today about is not only just directly Docker and Kubernetes, because we need to understand some concepts before we start the practical part. And this is why, because I made the same mistake and I started with these two technologies without having any theoretical knowledge. And I was lost for the few months in the beginning. So I decided to take a look into the architectural setup and all this theoretical stuff. So this is something that's very, very important. If you don't know what Docker and Kubernetes has in the background, like the machinery that's driving it, then it's going to be a problem. Um, there's actually a lot of things to cover. I managed to get what's most important in these slides. But of course, if you want to always learn more, everything that you see in these slides is taken from the official documentation for the two technologies. So before that, I think we should introduce first a little bit the concepts of service-oriented architectures and the microservices, which is the uh, basis of DevOps, and it's something that's very popular nowadays. So I believe that I managed to make something quite short about this in the first 15-20 slides mostly, so I think it's quite understandable. But please, if there is something unclear or difficult, just you can stop me and ask a question. I think I have control over the chat as well, so yeah, I guess that should be fine. I can see your messages, so if you have anything to ask, just type a message and we'll check it out. Um, okay, so we can start actually. Um, so the lecture will be divided in 4 parts. Let's call them like that, because we can't really cover everything at once. So first we will introduce the service-oriented architectures and the microservices. Um, and then we will see what's the difference between monolithic services, service-oriented architectures, and the microservices, as well as I will mention something about serverless architectures. This is something quite new, and it's becoming quite a thing. So all the cloud providers, they're aiming for something like this. It's literally saving them a lot of money and also providing people with optimal service, so you don't really have to pay for resources that you don't use. So we will talk about it later a bit. Then we will proceed with Docker. So I believe that we can make actually 1 or 2 breaks. We'll see how far it goes. We can make 1 break before Docker and before Kubernetes, because the biggest topic of discussion in this case is going to be Kubernetes, as I believe that you have some small knowledge of Docker already. So I will just cover the most important concepts, and then we'll proceed with Kubernetes. So Kubernetes has a lot of things. It's a super complicated system. It's not something that you can learn overnight, and definitely not from the slides. Until you don't jump in the water, you will not learn how to swim. The thing is that you need to practice all the time. You need to use it on a daily basis if you really want to keep up with the things, and the things are being developed. So it means that in the next probably couple of months, all of this is going to be new, and what we are learning right now is going to be a little bit obsolete. However, the lecture is updated from what's in the current state, so you're getting the best possible information about Kubernetes in this case. Um, so I will talk also about some SDN and software-defined networking shortly, and some communication within microservices, which is, I think, the most important thing in the whole agenda. And then, of course, automation and self-healing. This is something we all like, and it's quite interesting. It's very easy to do with Kubernetes, but to get to that part, you really need to understand everything in background. And in the part 4, we will just do practically everything. So today we will do something around Docker, because you need to understand the container platforms first before we jump to Kubernetes, as Kubernetes is the orchestrator of container platforms. So we will deploy some app. I will try to keep it simple rather than complicated, because in these things it's very easy to get lost, as they are quite abstracted. And we will start deploying some web server. I will try to explain you how load balancing works. We will do some reverse proxy, SSL termination, although I don't have any certificates, because CertBot will issue some certificates for domain, but nevertheless, we will just I will show you how it's done. So in case you need to do it for your website or something with Docker, it's very, very, very easy. Then we will see how this compares to Kubernetes, what you can do in order to automate this a little bit. And you shouldn't take it for granted, because sometimes you really don't need to use Kubernetes. It's just a matter of your um, perspective and your company you're working for. Sometimes you're quite fine only with Docker or even without. So not always it's the best choice. We'll see also later what that means. So first, let's start with a bit of theoretical approach for this. What is service-oriented architecture? It's a very simple concept that dictates what actually is going to happen in a company based on dissected services. So all these services, let's call them like that, they're deployed in different variants. So you have a platform on which you're deploying these services, and this is based on some sort of process. So it has to have a meaning in the company to do some business process, or to be dedicated to a department. And of course, these processes are being operated by users, and these users are using these services. So in order to do this, there is a term called best practices. For example, if you deploy a website, a best practice would be putting SSL certificate for your website. Just a small example. The key component in a service-oriented architecture is that services communicate with each other through a network. So they're interconnected through either physical or SDN network. So this is a very important thing to remember. That depends on a company, of course. You will hear different definitions of service-oriented architectures, like Microsoft will tell you different from IBM, from Cisco, etc. So it really depends on what the company is implementing. What is the most important parts of service-oriented architecture? So the service-oriented architecture is layered, and it should deliver business values, strategic goals, intrinsic interoperability, shared services, flexibility, and evolutionary refinement. So these are the core values. So it means that if you really want to achieve specific goals, you need to adjust these, let's call them approaches or ways to correspond to your mission. So that's why this is easy to be adjusted, because you can have services based on different layers. These layers can be, let's say, business services, enterprise application services, or infrastructure services. So these can be divided in your company based on the teams. So first you have the users, then you have the services teams, the developers, and you have the infrastructure team. So this can be sometimes merged into one. This can be divided even into more granularity. Sometimes the infrastructure team is only working Kubernetes, but you have a special people dedicated for the data center and security and the physical hardware. So it really depends on what your company is and how you do the stuff. So the actual roles in a service-oriented architecture are a service provider, a service broker, and a service requester or consumer. So you have the provider of the service, the intermediary, and the one who's utilizing these services. it's explained, as you can see here, that the service provider works in conjunction with the service registry, debating why and how services are going to be offered, the security and stuff like that. The broker actually makes information regarding the service available to those who request it. So it's an intermediary in this situation, and the requester is the one who utilizes the services. So this is the cycle. When it comes to implementing the service-oriented architecture, there's a lot of ways you can do this. One standard, it's called the SOAP, or Simple Object Access Protocol. It's a messaging protocol specification for exchanging structured information in the implementation of web services in computer networks. So one other type, which is quite popular, is REST. I think most of you have heard about REST, as it's becoming quite a thing for developers nowadays. And of course, it's been used in OpenStack in every environment you can imagine. It's quite popular. So this is why APIs like this are allowing different architectures to interoperate between each other. So even if they're independent of each other, they can still work with each other. Why the service-oriented architecture is important? So as you can see from the picture, before the service architecture, we had a very simplistic and monolithic ways of deploying stuff. Whether this was financial, business, or any domain, everything was very simplistic. But later, we started making more granularity in order to control services. And as you can see, some services can be reused. So if we do this, we can have better utilization of the services. So it means that if that's the case, then we have reduced costs in the business. And of course, scalability. So it means that you can scale this type of architecture much better than this one. In this architecture, you will have a lot of unused idle resources. So with microservices, for example, this is even more granular, and it allows you for even more flexibility, more reusability of the resources. But of course, everything has advantages or disadvantages. That doesn't mean that this is the best approach. Sometimes the best approach you can have is a monolithic approach. Depends on your company and goals, of course. What does this mean for cloud computing? Well, the service-oriented architecture and cloud computing are being developed together, so to say. They're meant to work together. So the problem is that some aspects are not being tested and not being evaluated. So many companies are facing the problem in decision whether to move their application or storage to the cloud, because not always this is the best solution. Sometimes they're concerned about security. As we know, in cloud computing environments, the multi-tenancy can be a substantial security caveat. And in this case, I think it's much better to keep your local data at your data center and move some of the operations in the cloud. So this is usually referred to as a hybrid infrastructure, because it uses some cloud computing and on-premises solutions. So if you find yourself in a company which does hybrid solutions, which is very, very common, you're going to have to know a little bit more about this stuff, as well as the mission of the company, in order to do your job properly as a IT person. So unfortunately, even if you don't want to be involved in the management, you will. So what's the difference between the service-oriented architecture and software as a service? This is becoming sometimes very, very confusing for people, because we know what's platform as a service and infrastructure as a service. But let's take Skype as an example, because Skype is a software as a service. In service-oriented architecture, you have stuff that are not present in the software as a service. So you have the abstraction, the governance, the registry orchestration, interface definition, the service bus, and dynamic recovery, as well as the reuse. So it's a thing that doesn't happen in the software as a service, but the multi-tenancy, service catalogs, and all these things, monitoring and service level agreements, they're all part as the agenda of both management models. The advantage of the software as a service is that users don't have to install and maintain software. In a software-oriented architecture, they kind of do. So in case of software as a service, is just install the Skype and that's it. In the background, all of that is being managed. So what's the idea behind these granular approaches? It's that you need to utilize what you deem necessary, and what is not used, it shouldn't be used. Simple as that. So you're just using the stuff that are being used. And this is how it should be. And this is how actually most companies don't actually make efforts to think about. And this is where their problem lies the most, when they start losing money. So you have to just consider every small aspect. And when you have granularity in your approach, then this is much easier to be accomplished. So what's the difference? What is microservices? Everybody's talking about it. Everybody wants to do Kubernetes, but it's not simple. As you can see from this picture, the service-oriented architecture as a model, it has maintenance of application servers and the application per se. But the application and the application server in microservices is merged into the services and the APIs. So you don't really have full control over that. You need a special team who's gonna manage these things, and this team is getting lost on the managed runtime environment. So let's say orchestrator and infrastructure provisioners and things like this. This is where things start getting more complicated in the microservices architectures, especially when you start talking about hundreds and even thousands of containers. That's where Puppet and Docker stop working, because you need something more comprehensive for that. So the biggest difference is not only what we've seen in the previous example, but uh, I think the biggest difference is that the service oriented architecture is putting a lot of stress on the business functionality reuse. So you can reuse some sort of uh, resource, but the microservices actually doesn't do much on the yes, the reuse is quite an important thing, but they're putting more importance of the concept of on the concept of bounded context. So what is this? I've put a slide in the end. This is a paradigm in the software engineering, and what it says. It says that bound context is a logical boundary, so it's not something that's represented as physical. When both subdomains and the core domain are defined, it's time to implement the code. So bounded context defines tangible boundaries of applicability of subdomain. It's an area where a certain subdomain makes sense, while others do not. It can be a talk, a presentation, a code project, or literally anything. So it's a very difficult concept to understand, more or less. So if you want to read more about this, of course, that's. But this is what makes the actual difference between service-oriented architecture and microservices, because in microservices you don't really know what's going to be reused. You assume that everything is going to be reused, and you come to the point where things have to be more granular, more divided. So that's why you have more focus on decoupling, and in service-oriented architecture is all about reusability. So it's even more detailed. And of course, there is another also interesting uh, let's call it advantage, because in microservices there is a strong focus on DevOps and continuous delivery and integration. So this is something that's possible in the service-oriented architecture. It's being done. I think Red Hat with their PowerShift platform as a service, their OpenShift, they're doing a lot of uh, DevOps continuous delivery in the model of service-oriented architecture. So it's possible. And yeah, so actually this is subset of this. So if you see the actual difference, it's very similar, except in microservices we have something extra than in service-oriented architectures. Let's put this in full screen. So while the microservices and the service-oriented architecture are similar, there's a lot of differences between them, of course. So I can cut short of this and go directly to pictures. These are additional information for you to read. So of course you can get some more information and understand this in better detail. And when you're doing interview, this is going to be very, very useful, trust me. So it's very good to know these things. It looks a lot, but this is also very important. The most important to understand is that not always one or the other approach is going to be the ultimate for you. So it depends. It depends a lot on the mission of the company, because the workflows in the both are different, and of course the outcomes are different. So there's benefits and of course disadvantages, and you should know this before you proceed to decide which approach to use. Of course, this is being decided by the CEOs and the leaders, and of course with the help of the people who work in the sector. So you will probably be responsible for helping your boss bring business decisions based on your experience. So it's good to know these things. A little bit about serverless architectures. So what is serverless? It's also known as function as a service. So this is even a smaller element, a smaller component, let's call it. So the applications are broken down into individual functions that can be invoked and scaled individually. So let's say, I think if you heard about AWS Lambda, this is a special place where you can instantiate your application. So you're not going to pay for a VM, because in the Amazon Web Services, you pay per virtual machine. So doesn't matter if you're going to run, let's say, Nginx web server on the virtual machine. The Nginx web server is not going to be up all the time. So it means that it's not going to make load 100% of the time. So your virtual machine will be on load when the website is accessed. In order to save you some money, this approach is only going to bill you when the actual web server is going to be running and making load. So the less load, the less usage, the less billing you have. So literally you don't pay for stuff that you don't use. This is the beauty of this granularity in the approach. But of course, this has its own disadvantages. If you focus purely on individual functions in your application, then there's high probability that you can miss the bigger picture, or if something happens in the terms of upscaling, and if your application is not, it doesn't have the possibility to scale up, like in the case with microservices, then like happens now with all these services, everybody needs to work from home, and Skype and most of these software as a service platforms, they get overwhelmed because they're hosted somewhere, and everybody's accessing them from all over the world, and meetings become literally impossible. The quality of your meeting is going to degrade, and you're not going to be able to scale. So that's why these things are being done, for the sake of unpredictable outcomes. So what's the what is serverless microservices? There is also a possibility to deploy serverless infrastructure in a model of microservices. So on Amazon AWS, in the Lambda, you have serverless microservices where you access the actual API gateway through the interface, which is your Amazon CloudFront. So literally through your web browser, you can instantiate a database or something else, Amazon Aurora, and you will have a database serving some site or somewhere else in your data store. And the database is something that you pay for, and it will be used as much as you pay for the database. You don't really pay for the whole instance or wherever this is running. So that's the actual thing. It's much cheaper, and you just pay for what you need to pay. Whereas if you're doing some other approach, then yeah, you're gonna have to pay even for stuff that are working in the background, and you're not using these. So these are some small insights to know about this. So let's proceed with the container platforms, and let's see what we can talk about this, because there's a lot of things to cover, and unfortunately I can't cover everything in one class. That's why these things are being taught in the course over year or 2 years. So when you're getting trainings for Docker and Kubernetes, this can last for a long time. But the best way you can do it yourself, and I will show you later how you can try to do some practices yourself, because there's places where you can do this by yourself without breaking a sweat. Before we proceed with Docker, I'm going to talk a little bit about virtualization, because of course virtualization is the most important part of everything. I don't know if you've had class before where this was covered, but I will cover it anyway, as it's good to repeat and to cover some stuff that's probably missed. So what is virtualization? It's the process of running virtual instances of a computer system in layer abstracted from the actual hardware. So I believe that most of you have tried VirtualBox or VMware or some of the more famous hypervisors. It's nothing special to talk about too much when we talk about containers, but we have to see the differences between standard virtualization and container virtualization, and how it works on which layers. So in the normal virtualization, we have a hypervisor, which we don't have in containers. In containers, we have a container daemon or engine in Docker, for example. So the hypervisor connects directly to the hardware and allows you to split a system into separate environments, VMs, virtual machines. So the VMs, they are hosted on a host. So it means that your physical hardware or the Windows PC or the laptop is going to be called the host, and the virtual machines using the resources, sharing the CPU and RAM, they're going to be called guests. So they will have the possibility to share CPU, memory, storage, networking, etc. So that's why the virtualization layer is split into different concepts. Storage, virtualization, memory, CPU, we'll see this later. So in terms of virtualizing applications and hardware, let's start with hardware first. In the past, you could just instantiate your mail servers, web servers, and legacy applications on different physical hardwares, but now you can reuse the same hardware and you can split it in different portions, and then you can instantiate these applications on each virtualized portion. But this has also of course, pros and cons. When somebody says virtual machines are better than containers and vice versa, that's an eternal battle, and it's never going to stop. And it's very wrong, because what's telling people what's better, running on fresh air or running on the sun? So it's like kind of you don't have the answer for that. So the only answer you will have is in your use case. If you're sensitive to sun rays and you have Lyme's disease, then you have to run in the dark. So it doesn't really matter for you what's better. What it matters what works for you. So this is the same case with containers and virtual machines. So how does the virtualization work actually? The hypervisors, let's call it software. So this software separates physical resources from the virtual environments. So the hypervisor manages to take into something that's encoded into the hardware, so the hardware function, and make a virtual function out of the hardware. So this is the easiest way I can explain it. So I believe that you've managed to try something like KVM or even the virtual box. It uses KVM, and you have other types of virtual machines there. So you can try also in OpenStack. It uses this QEMU virtual environment. So you can adjust this according to your needs. And there's different types of virtual disks you can implement, etc. Then the hypervisor also takes resources from the network card. It places a virtual function in this network card. So this is usually done with something called single root input output virtualization, and this is produced by Intel. So this is a function of the physical network interface card translated into a virtual. So when the virtual environment is running and the user of program issues an instruction that requires additional resources from the physical environment, the hypervisor relays the request to the physical system and caches the changes. So that's how this is done. There's lots of types of virtualization. So we will mention all of them actually. You have data virtualization. You can translate only the data that you need from your host directly into virtual portions. This can be usually some big data, or I haven't worked much with data personally, but I know that some companies are doing this, probably storage and stuff like that. Then you have desktop virtualization. It's a classical example. So the desktop virtualization is actually allowing an admin to deploy simulated desktop environments to hundreds of physical machines at once. So you can access this through browser or through application or through remote desktop, or depends on which operating system is instantiated. But in general case, this is how things are being done. I'll just check the chat quickly because it's not here. It's okay. Everything's fine. So we can proceed. So in terms of virtualizing the desktop, this is a very common practice in many companies, even at our university. So the Windows machines that you have, they're being administered remotely through, I think they're using LDAP or something like that to assign the users. And this is being installed remotely. So it's a similar approach to this. Server virtualization is also typical, of course. This is something you might want to know as well. Despite we talk about Docker and containers, this is also good to know. We're not going to cover how-tos in this section, but yes, so this is how things are being done in OpenStack, for example. So the problem is that you can't do DevOps with this. It's kind of not working, because spawning a virtual instance of a machine is not going to work as fast as a container. So this kind of agility is lost, and this doesn't translate directly into advantage for the DevOps paradigm. But if you want to virtualize, let's say, operating systems, sure, this is also possible. This is being done at our university. So the sysadmins are allowing people to access virtual hosts. I think you have some sort of VPNs to this kind of environments. I haven't tried this to be honest, but yeah, there is definitely Windows or even Linux platforms you can access through some channels. So they do this at the OsloMet as well. This is something I do, for example, network function virtualization. So this is also virtualizing your network resources from the physical domain. So if you have SFP plus or optical network fabrics, you can separate this later into VXLANs. You can separate it into SDNs, into container bridges, literally whatever you want on the virtualization plane. So as with other hardware, virtualizing the networks will reduce the cost you need to pay for devices. So if I want to create an edge router, I can do this on a physical machine with a good network card, and I don't really need to buy a edge router, because edge router can cost you a kidney. It's very expensive equipment, and this is something that's driving 5G. That's the strength of 5G. So just so you know that 5G is relying heavily on virtualization, and everything that is being done to make this virtual routers and switches is because in 5G it will save a lot of investments into hardware, and the telco operators will not have anymore the requirement to upgrade their hardware in order to keep up with the competition. They can just instantiate new instances of the virtual functions, and they will have a new router, for example, a new switch, bridge, or call redirection switch, proxy, or whatever it is, load balancer. So this is the beauty of virtualization. So these virtual functions, you can't do them into containers, because the containers are not communicating directly with the physical hardware. They don't have hypervisor. So the container can communicate with your kernel from the operating system, and that's where the distinction lies. So in order to have containerized virtual function, there is a way to do this. I have tried and it works. So for example, in Docker, you can instantiate a virtual machine with a plugin called VIRTUALIZATION. So the VIRTUALIZATION plugin allows you to run a virtual machine in a container, but we're not going to go that way. That's too much. So containerization is the virtualization with containers, as we know. What's the difference? So what is a container? When somebody asks, what's the container? The container is a virtual runtime environment that runs on top of a single operating system kernel and emulates an operating system rather than the underlying hardware. So this is a container. And the container engine is actually what's managing this environment. So there are hybrid container architectures. These are very common. This is something I'm practicing as well. So you will find yourself mostly in containers and virtual machines world pretty fast if you start working in a bigger company. So young companies, they start with Docker, with all this fancy stuff, but if you're maintaining your own infrastructure and you need to do some additional stuff, then you're not going to just work with containers. You're just going to work with everything. That's why the DevOps buzzword is very vague in my terms, and I believe that this means that you need to be a superhero. So if you apply for a DevOps job, you better be ready to know everything. So that's how it is. So what's the difference in the virtualization plane between container virtualization and virtual machines? Of course, it's the hypervisor, as you can see. In the virtualizations via VMs, you have a hypervisor, let's say VMware, and VMware communicates directly to your CPU, and it has to have a host. Sure, it can be operating system, it can be literally anything. So it can be some sort of edge location, and these things are going to be much smaller, because in edge platforms, I'll mention something about this later as well, you will have very, very small runtime environments which need to accommodate some small functions. It has a specific application. In multi-core processing, as we all know it, you have different cores situated in a processor, and these cores, they share cache memories. So this can be divided between the VMs, of course, and of course between the containers. But the division between the resources are divided in a different way. The way the hypervisor is doing this is it's flagging physical locations of the cores in the CPU to the VM. But in the container, they're doing this through something called resource quota sharing. So the container doesn't know the physical location of the core. It can only know details about the core through the kernel of the operating system, which can be Linux, Windows, doesn't matter. So through resource quota, the containers get as much juice as they need. If you just leave it by default, containers will have a contention between each other, and they just assume that they can use the whole power of the operating system. So if you deploy one container on Linux, it will use all resources it gets. So literally doesn't have restriction by default. This can be done with policies, and this is usually done with Kubernetes, and it's much easier to implement rather than in Docker. So we'll see about that later as well. So where are containers and VMs on the multi-core platform hardware? So the virtual machines emulate hardware, containers emulate operating systems. Just remember that. That's the only thing you need to know for now. The containers communicate also with VMs, so it's possible to instantiate containers on VMs. It's possible to do it the other way around. Everything is possible nowadays. It's not possible to run a physical processor in a container. That would be too much. So maybe that will be possible someday with quantum computing, but for now we have lots of possibilities. To be a bit more detailed, I will just go shortly through this so it doesn't become overwhelming, as already it is. So what does the virtualization with container does? So when you instantiate a container through your engine, it's Docker, let's say. It can be LXD, it can be Rocket. So Docker is not the only option that exists out there. It's the most popular one, but not the only one. So you're using container virtualization, and this is communicating through the cores, through the kernel. And the kernel defines namespaces, control groups, C Linux or whatever it is. It can be like a specific policy that allows the container to access from the core. So these are flags which do not translate directly to a machine code. So the only machine code that's been happening is between the kernel and the physical CPU. So in this case, we have a 4-core CPU, which is quite old. If we talk about CPUs, you have L2, L3 cache. We have the system bus through which the CPU communicates with the memory controller, the input-output controller, etc., etc. We are not getting into physical architecture. So that's how containers communicate with the cores. And you can have a monolithic approach, container per core, single-threaded way, or you can just allow the container to use all cores. There's a lot of ways this can be done. So application is usually divided in different containers, and this is usually most often one application, because you're running a single application in 4 different containers, and it can be a search engine with database, the search engine, the monitoring, and collection. So all of this run as one app installed directly on the operating system. And of course, they're using different cores, so the resources are being more strictly divided. So they're not going to fight for core per time, per different interval. This is a hybrid way. So you can do something like this. You can have a hypervisor. That's how we do it in OpenStack, actually. It's more of a hybrid approach, and that's how we're going to do it. So we instantiate an instance, and the instance has Linux, for example. And here you're running some applications. It has to have something on the VM. It just can't run a bare operating system. But on top of these, you can run something else. You can run a container engine. So you install Docker in the VM of OpenStack, and then you deploy things in your containers rather than directly on your VM. This is the same. There are disadvantages from this approach, advantages as well. One of the disadvantages is that if you're not careful, this can easily go very wrong in terms of performance. So you're adding a more overhead to the processing of the virtual machine by running a container engine, because the VM not only has to take care of itself and running its own OS, but it has to run also the container engine. So running the container on bare metal directly, it's kind of better. So rather than this, but not always you have this possibility. So you have to sacrifice a little bit from this performance overhead. This is measurable. If you plan to do a master thesis in the future, you can also try to measure what's the difference between straightforward architectures and running something like this, or just something different. There's a lot of ways you can perform research. So this has been already researched, and it's a matter of discussion all the time. And there's plugins and solutions being deployed to circumvent these options. I have also some suggestions that I will show you, especially for the network, because that's my specialty rather than storage or data. So I can show you in terms of communication how you can reduce the overhead and run the containers on top of VMs, more or less like in the style of running directly on bare metal without any virtualization plane. It's near lossless, let's call it like that. Pros and cons, sure. I added a lot of text here. You can have a lot to read, and it's very good to get to grasp what's the difference. Let's call it first about scalability, just for a matter of perception. A single container engine can efficiently manage large number of containers, enabling additional containers to be created as needed. That's what's the difference. So in security, there are pros. Let's say this is also highlighted in black because security is a pro and a con at the same time of the containers. So the modular approach architecture by the containers can make it more difficult for attackers to attack your infrastructure. But at the same time, if we look at the cons, the security can become a problem because you will have more pathways that are exposed towards your lower level hardware. So the isolation becomes an issue. That's why containers are secure, but not by default, like VMs. So the VM is secure by default. And if you don't pay attention to security, in the default state, the VMs will be more secure than the containers. But if you take your time to think about the infrastructure, you can always secure the containers pretty well and achieve a decent level of isolation. So this is something to think about as well. And I will share these slides with you after this. So I will also provide you more information than only the slides, because this is quite an interesting topic, and it's very interesting to discuss and to work on and to have fun. So the containers can also be very tricky to handle. That's a warning, because if you do a lot of Docker and a lot of containers, this can easily start becoming super complicated, and it will require you to use more complicated means like Kubernetes or a swarm, and orchestrators, like we're using something called MANO, management and orchestration. And this is a huge framework that encompasses software defined frameworks like Open Daylight. Open Daylight is a networking plugin, let's call it a plugin, but it's as big as OpenStack, which is integrated into OpenStack to serve massive amounts of data and devices, and it's used for 5G. So these things are very difficult to manage even with Kubernetes. So what you always need some sort of machine learning thing to manage this stuff. It's out of our comprehension, and it's too big. So if you're doing microservices like that, it can easily become your enemy, because you'll get overwhelmed, and it's not going to be easy to serve everything just in one click. So I think we can take a short break, and like maybe 15 minutes, and then we'll start with Docker and the containers. Let me check the the chat if there is something here. Yeah, everything looks fine. So if please, if there are any questions, just type in the chat or interrupt. I'm listening, so you can always ask. We'll continue with Docker, like maybe in 15 minutes, so 10:15, we'll be back. Then after we finish with Docker, we'll go with Kubernetes, and we will have some practical demonstration. Yeah, let's proceed slowly so we can cover what's Docker and start with Kubernetes later. So I believe that most of you have tried Docker so far, maybe from the previous lectures and classes or by yourself. So you're aware of what it does and what is it about. But nevertheless, I will just cover some essential things about it, maybe something new for you. In any case, it's good to mention about before we go practically. So what does Docker do? The Docker uses the containerd runtime environment, unlike the Linux containers, to run its Docker engine. So the Docker engine is the proprietary part of Docker. That's what making it different than other container platforms. But what's common for them, they still use the namespaces and the C groups and the app armor of Linux in order to communicate with the Linux kernel. So in containerd version of Docker, let's call it like that, there are small daemons, small services more or less, that run in the containers environment in order to connect it to the Docker engine. So this is more straightforward approach. It's a little bit more complex than what the libLXC offers, but that's what it makes it very different than others. What does that mean? It means that earlier. So it means that the Docker engine is launched somewhere 2013. It's open source as well. They have a enterprise version of the software. But in any case, Docker is evolving very fast. It's running on different environments nowadays, and that's what making it quite powerful. So you can have it on Linux, Windows, you can have it on bare metal, clouds, etc. So it's very, very good, good stuff to know about. So the lib container, the library for containers, it was open sourced by Docker, and now Docker managed to donate some stuff like the image specification and also I think it was some stuff related to the run C. They just opened everything to the open container, yeah, exactly, to the open container initiative to help the standardization of stuff. So it's becoming industry leading standard, and for a reason. So people worked very hard to get to that point. And of course, I forgot to mention earlier, if you want to get some additional information about these things, you have the official website's link and the containerd um, links on the bottom of the slides, so you can access them later. I will share this in form of PDF with you. So when we talk about some technology here, I will provide most of the links and relevant information down, so you can read more about that, because we can't cover everything in detail. Installing Docker is very simple. I think I've shared this slide with you earlier. So if you're installing it on Ubuntu 16.04 or 18.04, you have to use these commands. So I have to mention some small detail. When you install Docker like this, you're installing the community edition. The enterprise edition is something you need to pay for. So in the enterprise edition, you have stuff like image verification and scanning and additional things like that that are not supported in the community edition, because when pushing images to registry and some repository you have online, like the Docker Cloud, Docker Hub, you actually don't scan your image. So the integrity of your image can be compromised. You may have a vulnerability in images, and you're just deploying an insecure application. So this is what Docker does for you. They perform security scans, and you pay for that service. So that's how things are. And usually it works because everybody wants a security scan, especially when you're running something serious in production. And there is an installer for Windows Desktop. Feel free to run it. It works great. And there were some problems in the past with networking, but nowadays everything is solved. So it works on Mac and on Windows. So just feel free to follow this link and check it. It's awesome. So I'll try to go through concepts of Docker quickly, because there's also a lot of things to cover here. I can't cover everything that's from documentation, but the most important parts. So the Docker engine has a server, and this is a program. It's a daemon process, more or less. You can restart this Docker daemon. So on the top of the Docker daemon, you have a RESTful API. So the REST API is specifying interfaces that you can talk to the daemon, and these are done through command line. So the Docker has its own command line interface and syntax. So we'll go through that also a little bit, but of course we will not be able to cover everything. So this remains a lot on you to practice and try stuff. That's something I can't do for you, unfortunately, and it's something that you will have to do yourself. So the command line uses the RESTful API to interact with the daemon, and the daemon creates and manages something called Docker objects. And these objects are images, the containers itself, because the containers are based on images, data volumes, and the network, and that's it. So these four objects are the most crucial components of the runtime environment of Docker. So the data volumes decide which part of the disk is going to translate into volume on the container. The network interfaces, whether they're going to be breached, whether they're going to use other plugin. You have lots of plugins like Mac VLAN, IP VLAN, overlay plugins for running clusters. You have VXLAN, and you have Calico plugin for BGP. I'll talk about that one. That's, I think, the best option you can use so far. So there's literally everything, and the possibilities are endless. What is the architecture of Docker is that the Docker daemon is the heavy lifter. So literally the daemon is the one who does everything. So the daemon is taking care of the images. It's taking care of connection to the registry, whether it's going to be the Docker Hub usually, because in Docker Hub you will make your stuff and pull your images there, push and pull images there. So later you will create an account, and I will show you how to use it. So you can have your own web servers. You can have your Ubuntu image, literally whatever you want. I have my 5G core network in the Docker Hub, so it's like 11, 12 gigabyte container. It's insane. So the Docker host is the computer from which you're running the daemon. Literally, it can be VM, it can be literally anything. It can be a Amazon instance, OpenStack instance. So on that instance, you will have the daemon controlling your images and containers. So you're gonna do command line interface commands. So when you initiate these commands, they will just tell the daemon what to do. Docker build the image, pull the image from the registry, run the container, etc. So that's how these things are done. So yeah, this is what I just said. What I need to know from you is later whether you created a Docker Hub account. You don't have to per se, but I will strongly suggest that you do. You will use it all the time. I still have it as I created it years ago, so it's not something that's bad. Later we can push some image there and you will see how it works. You can use it also for continuous integration and delivery, as the hub offers you to connect your GitHub account together, so you can have version control and rollouts, rollbacks, etc. So this is priceless. I think they also offer you one private repository for free, so you can have a free repository that's disconnected from the rest of the world, and you can just put your uh, sensitive stuff there. Uh, so when you use Docker, you're creating and using images, containers, networks, volumes, plugins, and other objects. And this is just a brief introduction of these things. So this is additional information, so you can read through it. What is most important that in the exercise I provided for you, you can create a Docker file, and you can define the steps in the file, how the image will be created. So when you run this with Docker Compose or somehow else, it will just create an image that will be what you need for. So this is a very comprehensive way of doing stuff, very fast and small. So you don't need to run big workloads. And the container that runs, they will be the running instance of an image. So the image has to be on the host while the container runs. So you can't really delete the image as the container is running. So you can stop, move, update containers, delete, access the containers inside, etc. So by default, the container is relatively well isolated from other containers and its host machine. They communicate with other containers at the network because they're bridged together in a bridging interface. So they simulate layer 2 network. So they will have the same layer 2 segment. So they just share the same bus. It means that the only way you can access the other containers is through the host. But that's not a secure way. It means it's well isolated, but still not secure. In order to secure this, you need to provide policy of access. And this is not something done by default. And it's not supported with on a network layer with the default interface, which is bridge. So you have to use other types of plugin for this. I can also show you later how we use a plugin called Courier, and this plugin is integrated in the Docker daemon to communicate with the OpenStack's Neutron through OpenStack's authentication called Keystone. So Keystone authenticates the Docker plugin called Courier in order to run containers in your VM inside OpenStack that communicate directly with the software-defined networking of OpenStack. So this is not something easy to perform, but there is an option like that. So literally, there is everything. So you just need to find it and use it. This is how you run a container. I believe you tried this so far. And with this command, there will be a Ubuntu image run. So if you don't have the image in your host, it will be pulled from the official repository from Docker, and it will run an empty Ubuntu image, so you can access it. This command will enter directly in the image while it's running. So -I -t means you're running it in interactive mode. So if you put -d, which is something you always want, it will run the container as a daemon, so it will always run. You can add flags like restart equals when stopped or always. So it means that in case the container stops, just restart it, or in case the container does something, just restart it if you put flag always. So there's lots of flags you can add in this. If you do not have the image locally, it pulls it from the repository. The Docker will create a new container. These are the steps, what this command does. It will create a new network interface. So by default, it creates a bridge. And it will start the container and execute the bin bash to enter inside the container, so you can install stuff manually and do something like that. You don't have to use Docker file. You can do it this way. So services, what are services? They allow you to scale containers across multiple Docker daemons. Let me check the chat quickly. How different container know each other names in Docker network? Okay, well, the containers don't know names. They have IDs. The container is given ID, and this name that you get on the container when you run it is for your convenience, for your command line. But the containers between each other, they don't do that. If you want to do that, you need to use DNS. So this is how Kubernetes does. It uses names, and it allows you to communicate with containers between different hosts and nodes. So this is more a matter of clustering, because if you don't do clustering, if you're doing some single or just some multi-container deployment, you're not using names, you're using IP addresses. And these IP addresses are, yes, please. So these IP addresses um, are resolved if you have a resolver, but this is something that you can set up, sure. Docker Swarm is like Kubernetes, and they use DNS in order to distinct between the containers. And there is something else I will talk about later. It's called service discovery protocols. So there's a lot of ways how containers communicate with each other. It's not just network level. So in the namespaces, the namespaces are like isolated spaces for the container. So this is adding to the question from before. So the namespaces perform this isolation. So when you run a container, Docker creates a set of namespaces for that container. So these namespaces are additional layer of isolation, and each container will run a separate namespace, and its access is limited to that namespace. So if another container wants to access that namespace, they will need to have a lot of information for it. So process ID, the network namespace, you have IPC resources, internet process communication. Then you have mounting file systems, and then you have UTS, which is a Unix time sharing system. So there's stuff like this that allows more granularity of control. The Docker engine on Linux also relies on another technology called C groups, control groups. What is a control group? The control group is limiting application to specific resources. So there are flags you can add to the container, or this is usually done with Docker Compose or with in a Docker file, because rarely when you will be deploying container from the scratch and just redeploying again, because you have to have some file to save this. And using Docker file, you can just deploy the same container and image over and over again without changing stuff. Or you can upgrade it as you go, and you will have the file there always to run the same container at any point. No matter if it's deleted, no matter if something is lost, you just delete it and you run it from beginning, and you still have the last working state. So in this file, you can define flags which will translate into the language of the C group, the control groups. So you will add resource management stuff, like how much RAM to assign for which container, how much CPU cores, how much power, etc. So this can prove very useful if you're doing load balancing, because then you will assign, let's say, more bandwidth for the database rather than for the search engine. So the container that's running the search engine of the website is not going to have unused bandwidth and resources running for him. So these small details are also something you can tweak much easier than in the case is with the virtual machines. So you can limit memory. This is kind of most common thing. So if you have limited RAM in your data center, this is a way to do this through the control groups. Then you have union file systems. So union FS, these are file systems that operate by creating layers, very fast, lightweight. We'll see how this works later in practice. So there's a lot of file systems you can use. These are just some. You can use AUFS, BTRFS, VFS, device mapper, but it's not limited to that. We will talk after your project too about Ceph and Cephfs. So I will show you how to use that with Docker and Kubernetes. It's not the simplest one to use, but I think it's one of the most powerful ones because of its clustering potential with working with object stores and etc. So we'll talk about that when time comes. So the container format, the Docker engine is combining namespaces, control groups, and the union file system in a wrapper called container format. This is what's known as lib container. So there's a plan for support other formats by integrating technologies like BSD jails and Solaris zones. I'm not sure they have done this now, but I think they will. There is something called Docker Compose. I don't know if you heard about Docker Compose. That's a way to run, let's call them multi-container applications. So you can do more manual approach of clustering rather than using Kubernetes. So if you don't need to run huge clusters or full-blown applications in that terms, then you don't really need Kubernetes. You can use Docker Compose. I just said it's more semi-automated way, which is partly true, but you can also pretty much automate everything with Docker Compose. You can use some scripts to automate the provisioning and build, etc. So with Docker Compose, you create a file. So the environment of the application in which it will run and the image in which it will be deployed is going to be defined in a file called Docker file. So when you have this file, literally you can run the same app everywhere. For example, this file will run a Redis service, and it will build the Redis service as a web service. It will expose the ports 5000 on your host and on your container. So you can put, let's say, translation of ports 8,000 to 5,000. So if 5,000 is taken in your physical host by something else, or 8,000 is taken by something else on your other VM or wherever you're running the container, you can expose other ports on the physical host to some port in the container. So when this port is accessed from outside, it will trigger a port 5,000 on the container. Then you can assign volumes, and these volumes can be from different disks, depends what volume you want to create, some logical volume 1, and it will be translated to var log. So everything you put in the logical volume 1 inside the container, it will go to var log blocks. Links, it means that you're using Redis, and where is Redis gonna come from? It's gonna come from image Redis. So if you use this, it means that you're not assigning repository. If I assign repository, let's say my name slash whatever I gave name to this image, it will pull the image from my repository. Otherwise, in this case, it will pull the image from the repository of Docker, the official one. And then it will assign volumes, the same one that we defined before to tell that you're going to use this volume. So this is more or less a simple example how you can run a Redis service just with Docker Compose file. So if you have this file, you just run Docker Compose up and it will run a Redis service. That's how simple it is. This is the beauty of containers. You just don't need to worry about anything. If you're starting deploying stuff on the go, this is the solution for you. Networking. So this is a very big topic, and I will try to cover as much as it's possible because this is something I can talk about the most. But I want you to know that the system of Docker is pluggable in terms of networking using drivers. These are just several drivers, but there's loads of others, and they offer different functionalities for the network. So the default driver for Docker is bridge. So when you run a Docker instance, it will run in a Docker bridge driver. So this driver bridges directly to the physical network interface card using Linux bridging, and it creates some IP tables rules. And this is how you get traffic forwarding between the outside world towards your bridge. So the latency that you get here is added overhead from the kernel in which the bridge is running, as well as together the physical network interface card. So if you're using low latency kernel instead of generic in the Linux, it can get some improvement in terms of communication speed. There is a host driver. So this tells the Docker to use the actual Docker host network card directly. So your physical interface card will be used directly, and this is available for Swarm services on Docker 17 and higher. You can use it for removing the isolation between the container and the Docker host. And this is something you can try also to see how it works. Overlay is something that's similar to bridge, except in this case it uses VXLAN. So the overlay networks are connecting a couple of daemons together, and this is only available in Swarm services. So when you're using Docker Swarm to deploy microservices, they will be mostly connected in this overlay mode, which is VXLAN. So the VXLAN is not the best performant plugin. You will have substantial overhead the more you scale your cluster, and your network will start suffering. The optional best performance you can have in terms of network in a Docker environment is using MacVLAN. MacVLAN is a plugin that allows you to have MAC addresses in the container, and the container is regarded like a physical device inside the network. So the container can have VLAN tags assigned to it and integrate with your physical switch. So you can have trunking ports, you can have everything you can imagine on a physical network to translate directly to the container. But you should be aware, because deploying this in a cloud cannot be possible, because cloud gives you a instant public IP address, and you can't really have a LAN address there for the container to have a MAC address. If you're getting only private address to the container without floating IP, then you can run MacVLAN. So the MacVLAN will tell the Docker also to broadcast Ethernet frames through the LAN network. So if you're broadcasting Ethernet frames, it means you have all the rules that apply for bridging, like STP protocol for spanning tree, avoiding loops in layer 2. Everything will apply also to this container, because the network the router and the gateway or the firewall will observe the Docker running MacVLAN container as a physical machine, as a computer. So this is also very fast, and it doesn't add any overhead to overlay networks and bridges. So that's, if you can use this, always use MacVLAN if you're having something in your local area network. There are third-party plugins. There is a possibility to use none. It means your container will be disconnected from networking if you want it as such. So you can only access it locally. So there's different options you can do. And these plugins are available from the Docker Hub. I provided a link here. You can check it. There are also lots of other plugins. They are all called container network interfaces. So it depends on what you're doing. You can interchange these. One of the plugins I use mostly is called Calico. Now, Calico is a BGP network plugin for Docker. So why BGP? Not because it's awesome or because it sounds like something crazy, but because BGP allows you to route between autonomous systems. So if you're connecting the containers with some legacy or any kind of networks, SDN networks or SDN controllers, it will work, because BGP is a protocol that allows multiple autonomous systems and segregation of networks in very big portions. So it's specially designed. The algorithm is similar to distance vector routing, and it allows you to have huge networks and enforce policy, which is very important. So when you have policy enforcement, it means that all the applications you're running in that container, or just a single application, if you're running in microservices, it will be very strictly defined what can communicate with what and what can be isolated with what else. So this is very important. To get more on this, because I can't cover everything literally, there is a link here, and you can take a look into this. It's a very good stuff, and installing the plugin is very simple. So I would suggest always, if you can use Calico, just use it. It's a good stuff. It's tested, and for me, it always worked the best. So now we can proceed with Kubernetes, and I'll have to introduce also some stuff before. This is a very complicated topic. It has also connection with Docker as well, with other container runtimes. But as itself, it's super complicated, as we're talking about a lot of things at the same time. First thing we need to talk about is the YAML language. I don't know if you have introduction to YAML or you know what YAML is. In any case, I will just give you small basic stuff here, so it can kickstart you into working with YAML. You can also check it yourself, of course. Maybe you know something, you can improve your knowledge, but you need to have some knowledge into YAML in order to proceed with Kubernetes. The same applies with Docker if you're using Compose or any kind of automation, because writing these files, it requires YAML. So this is very similar to JSON, but there are differences with JSON. These are markup languages, and yeah, YAML is not a markup language, kind of. That's what it means. The first meaning of YAML was YAML, another markup language. But then somebody came to a point when they were quite angry about that statement, and they said YAML ain't markup language. That's what YAML means. So funny, but yeah, that's how it is. There is information on the official website. Whatever you do, don't visit this website, at least for now, because it's a very messy, and sometimes even I get lost. So it's always better to just open YouTube and check what is YAML and how to work with YAML, because the website is very advanced. So it's literally, you have all the information required there. YAML is a data sterilization language. So what does that mean? It means that it's designed to work with continuous integration, continuous delivery pipelines, and open API specifications. So it's a declarative way of expression. So YAML is designed to be friendly to people working with data and archives, unique cleanness by minimizing the use of structural characters. So it's not going to be like Perl scripting or something like that, where you're going to get lost quickly. So that's the positive aspect. And of course, it's not like JSON, but it's in compliance with JSON. So everything that's written in JSON can be rewritten in YAML. And it's very easy to get a grasp if you have some knowledge in Python, because it's quite similar when it comes to the indentation. So you will find it quite good. This is some examples. For example, if you want to use some strings, you can write them like this: title, semicolon, space, introduction to YAML. So this will translate directly to this way of writing in JSON. The numbers also, so you don't have to put quotations, you just put the age and the number, the price and the number. So it's a little bit less complicated than JSON. For example, in JSON you can have something like piping stuff like this, npm CI, inverse, how it's called, slash, whatever it is. In any case, you can do this in YAML just by putting a straight slash and just putting everything in the next line. But indentation is very important. If this npm is one on the left or one on the right, this is not going to work. So the indentation is super important. Then you have booleans, you have null values, sequences, nested values. Everything is supported. It's just like another language. So it's this is only the basic stuff. If you want to get to the advanced stuff, you have to visit the website. There's a lot of things to get through YAML, but these are just basic to kickstart in writing Kubernetes files and also Docker Compose. Then, for example, you can have anchors. The node anchors are, let's say, in JSON, this gets a little bit more complicated. You have to get used to the parentheses. So if you don't close the parentheses, this gets out of control. It has to be indented. So that's where YAML starts shining in, because you don't really have to do that. You just put books, and in the books you can define 1984 and author, whoever it is, Animal Farm author, whoever it is. So you just put the books and the author. So this is super, super great. In the case of JSON, you can't really do it like that. So you have to open the parentheses and you just go on the next lines and another parenthesis and all of that. So by using parentheses, things become less ordered. So if you don't do this very well, and if you do a mistake like this, if you can see this, this is gonna mess up everything. If you don't see this, end of the story. You'll just try to find out what's the problem, and many times if you're tired, you don't see the difference between this parenthesis and this one, straight one. And so that's a problem. The same applies for YAML, more or less, but at least you're not working with parentheses and brackets, so it's everything's fine here. Okay, so after this, I think we should introduce a bit of clustering, because when you start deploying Kubernetes applications, most of this, not most, but everything will be deployed in a form of cluster. Cluster is a natural form of grouping entities and objects in a way that's mathematically sound. So there's different types of clusters. I'm not going to go through all of this. This is mathematics, and I'll just mention some basic stuff. And later I will mention about service discovery protocols, how they are connected with clustering, and why is this very important for Kubernetes. Everything that's in Kubernetes is based on these principles. So clustering is used for everything. You have clustering in birds, in galaxies, in ants, and everything that works in a orchestrated way is forming some sort of cluster. There's different ways clusters are formed, and mathematically it's formulated as a multi-objective optimization problem. So in network theory or in graph theory, clusters can be defined as graphs. It can be defined as also neural networks in machine learning. So these are just basic ways how things tend to work when they work in a group. So there are a couple of different types of clusters. You have connectivity-based hierarchical clustering. This is actually what Kubernetes does. This is how social networks work. This is how LAN networks work, how BGP protocol, OSPF works. Most of this is hierarchical clustering. Then you have centroid-based clustering. This is how galaxies work when you have gravity and planets getting around the galaxy. Then you have distribution-based clustering. So this is very good for statistics in distribution models. And when you have like a distribution, it's better to explain like throwing, let's say, some sand on the ground. And the way this is distributed is according to the center of gravity, and the most pieces will fall around the place where it's centered mostly, so it's kind of difficult to explain without a picture. Then you have density-based clustering, like sparse and dense areas, so this is how population control is being measured, for example. Then you have grid-based clustering. You're creating a grid in order to measure. Let's say you put a piece of blood on a examination table, and you put some grid in order to measure how many blood cells, red blood cells per squared micrometer or something like that. So there's a lot of different ways how clustering is used, and Kubernetes used some of that. So in graph theory, I believe that you have some graph theory in your bachelor level. It's a stupid math, as we call it, but trust me, this starts to follow you later after you finish your master degree and you go in a PhD or something. You will have to work with this for the rest of your life. If you're working with machine learning, data science, or literally anything, clustering will be everywhere. So what we said, expressed like this, it's a subset. Literally, cluster can be defined as a set and subsets. So in the real world networks and social networks also, the nodes create tight-knit groups characterized by high density of ties. So these are defined as literally subsets. They belong to something else. So it means that for a direct graph, if we have a graph E, it will be distinct from another graph E by that it has elements, or let's call them neighbors, that are existing more than in the next areas around him. So the neighborhood will be more tightly coupled than anything else. So the distribution is given by this equation. And I can skip all of this because it's meaningless to comment. In any case, this is just an overview that clustering is a very, very interesting topic also to discuss and to analyze, to scientifically research if you need to do that. And Kubernetes clusters, when it comes to IoT, they will be very interesting to research in terms of this, and also big data and machine learning, if you will. This is just a small C code. I just found some interesting example, and it's showing that the cluster coefficient, what is a clustering coefficient, is that the degree of connectivity between the green node and the other nodes depends on the link levels. So if you have 0, it means that they're disconnected. The cluster coefficient is going to be 0. But if you have clustering coefficient 1, it means everything will be connected with everything. So best example can be social networks, Facebook, or this galaxy that's moving around here in the GIF picture. So that's it's kind of difficult to explain without further talks and explanation, but this is the best I could give for just one slide. If you know C, then this is how it's done in C. I'm not going to go through this, of course. I even forgot C. It's been quite a while. So what does this mean for Kubernetes? So in simple words, Kubernetes is using clustering to deploy clusters. So clustering is a way of servicing the nodes deployed in microservices by using service discovery protocols and network connection. So one way to do this is like it's represented in the picture. So you have API or a gateway or a client, and you're accessing different services through RESTful APIs that are deployed in a pod, Kubernetes pod. And now, how to access which service? If you're going to load balance, if you're going to proxy this, what you can do with this? Literally, there's a lot of things. So there are two ways to discover services, service discovery patterns. It's a client-side discovery and a service-side discovery. So service instances, they have dynamically assigned network locations, because you can't really assign this statically. All these IP addresses of each service is going to be some random. It's going to be in a domain that you put in advance. If you add, let's say, 24 subnet 10.4.0.0.16, then both of these subnets will be used. So all the services will be deployed in that network range. And it's going to be mostly random if there is nothing else defined otherwise. And this is good for auto scaling, failures, upgrades. So you can manage a lot of stuff like this because you don't have to worry for a lot of other things. You just have to focus on keeping the stuff running and scaling them as you go. In a client-side discovery, the client is the one who is responsible for finding the network locations. So in this kind of request-related discovery, you just have to find which location it is. So I gave an example. For example, Netflix OSS. It provides server, actually client-side discovery. So they have Netflix Eureka, which is the service registry somewhere in the cloud, and it provides RESTful API for managing the instances. So it connects through your TV to the cloud location, and you need to do the request. So you're the one who's trying to discover the place, video on demand, all this kind of stuff. So that's just one small example of client-side discovery pattern. Then you have server-side discovery pattern. In these cases, most of the time you have involved some sort of reverse proxy or load balancer. For example, AWS, Amazon Web Service Elastic Load Balancer, ELB. That's an example of a server-side discovery. It's a router load balancer, and it balances traffic that goes to the instances from the internet. So the requests are queried to the service registry. It's a data store. It can be like etcd, something else, but in this case, you can use Nginx with Consul, or there's a lot of ways how this can be done. I can show you how to use Nginx with Docker, but for Consul and etcd, we're gonna need something more than that. There are some examples, of course. It's not simple to do, but this is how things are done most of the time. You need some sort of key value store, and Kubernetes actually does this most of the time automatically, and you can assign this in the YAML file in order to define some sort of load balancing, although there is by default. The load balancers work in different algorithms. So when you deploy something by default, it will use round robin to load balance. So it's not going to care if this instance is somehow overwhelmed. It's just going to come into its turn, and it's going to put the request to it, next request to this one, next request to this one, then next request to this one, then to this one, then to this one. So there are other ways you can also load balance. There's smart ways you can load balance, and these are called auto scaling, or more precisely horizontal auto scaling. In horizontal auto scaling, you're taking some sort of information, and this information can be usually input from the outside. So this input can be HTTP requests, and then you will measure with Prometheus how many HTTP requests each of these instances is having. So if one of the instances is overwhelmed with HTTP requests, you're going to proceed the HTTP request through the load balancer to the next instance that is available. So that's just one example. I can give you lots of other examples, but this is how usually it's done. So in what is a service registry beforehand? I talked about, mentioned etcd, I mentioned Consul. These are the two most common key value stores that are being used for service discovery. And yeah, they what they do actually, it's a part, the service registry is a part of, only parts of a service discovery, and namely just a database of the network location of service instances. So the service registry, it provides you high availability. So in order to have high availability, you need to have 3 or more nodes in general, although it's preferred much more than that. Depends what kind of services you deploy. In a monolithic architecture, for high availability, you need 3 or more nodes, because if one node fails, there should be always 2 between which the traffic will be load balanced. If you have two nodes, then you can have the problem of choice between two nodes. That can become a very big issue, especially in storage related functions. When you have object storage and you have only two nodes cluster, and then you copy data on two locations at the same time, and then you have the problem of reading from which location to read, because you don't really know which data is the next one. So it means that what's next? Did I save on left or the right side? So you have a problem. In this is very well evident in Ceph, for example, or other, or Gluster FS. You need a high availability cluster, more than 3 nodes. That's the rule. 2 is not going to work. So Apache Zookeeper is also one example. I've never used this because this is designed to work with Hadoop, and these are things that are mostly used for big data. So you can check that as well. The registration has a couple of different ways. The registration of a service can be self-registration. So the service registers itself to the service registry. It pushes some information like the name, I have this name and I have this IP address and this port, and I have this heartbeat, and I'm keeping that option to unregister if that's required. So the service, for example, the Eureka, there is a good example. It's the Netflix OSS Eureka client. It handles all aspects of service instance registration and deregistration. So the Spring Cloud project, which implements various patterns, including service discovery, makes it easy to automatically register a service instance with Eureka. You simply annotate your Java configuration class with enable Eureka client annotation. So this has some benefits, drawbacks. One benefit, it's simple. You don't need to do anything. You just let the service do its thing, but it can really go wrong sometimes. If you're running couple of different instances at the same time of the same service, they're called replicas, then this can become doubled. It can become difficult to implement in a framework by other services if they're being used in a microservice architecture. So sometimes it works, sometimes it doesn't, depends on your architecture. But then you have third-party registration pattern, which is most common, and this is being done by etcd and Consul. So the third-party registration, it does health checks each time. So there is a register, and this register is checking the service for its health, and it's telling the service registry about its health. It's like a reporter of the health of the service. So auto-scaling group in Kubernetes or in EC2 in Amazon is done this way. This is actually something difficult to configure manually. You can use Redis, you can use etcd, you can use a lot of things to make architecture like this. And if it's not pre-configured and built in the actual solution, doing this by yourself can be a nightmare. So doing health checks is a good thing. When you have a queuing system, you need also a service discovery protocol. You need some sort of local connection, and it needs scheduling. It needs a lot of stuff. So if it's not built like Kubernetes has it already within itself, then you're most likely not going to do this manually. It's very complicated, but this is the better way. So sometimes people just talk about the Kubernetes as the silver bullet, but it's not. So it means that you don't really need Kubernetes for many things. But if you want to do some service discovery and load balancing like we had that, then it has it. It's already built in, and this is something that's saving you a lot of time. Then storage orchestration, service orchestration, rollouts and rollbacks, automated ones. So this is something that you can do with VMs. This is something you can do just without using infrastructure like this. You can use rollouts and rollbacks, but not automated. You can use triggers. You can use third-party applications like Jenkins, for example, to create jobs and triggers in order to push code to your registry, pull code back, etc. This is done through automatic bin packing. So there is self-healing option. So the Kubernetes defines replica sets. It has a daemon called replication controller, which manages the number of replicas that are running inside the pod or in the cluster. And it makes sure that the number that you have defined in the YAML file is always going to be the one that's going to run no matter what. So it will kill containers that don't respond, and it will rerun them automatically. Or if some container fails because of some reason, this is something that happens in reality, it will just run it again. So you will have a super high availability, resilient cluster that fixes itself without your need to intervene. There will always be need to intervene no matter what kind of AI system we have, but Kubernetes halves this job. So it helps you a lot by saving you a lot of time and troubleshooting and things. You don't really need to troubleshoot what service went wrong where. There's possibility to save logs. There's possibility to save secrets and all of that. And the thing is that it will just do the job for you. You don't need to spend time in troubleshooting. So the Kubernetes is a very complex system. I have to talk about these things, unfortunately, because if I start doing things practically, it's just gonna be a huge mess. First, we need to understand what are the components of Kubernetes. So when you deploy Kubernetes, you get a cluster. That's how it is. It's a clustering software. So the Kubernetes is comprised of a set of worker machines called nodes. They are running containerized applications in Docker. You can use Rocket, you can use the Linux container system, but Kubernetes recently has a very nice agreement with Docker, so things just work out of the box. This is the good deal. The cluster is usually deployed at least one worker node. So what is a worker node? The worker node is the node where your service is running, and the host is where your master is running. So the worker nodes, they're hosting pods. Each pod, they're components that contain containers. So for example, this part here is the pod, and the pod is containing containers. This one has 2 containers, and this pod has 1 container. And they're interconnected with each other in IP addresses. So they have the same IP addressing domain, 10.10.10.0, and they're connected together in a service. So the green area, it means that they're comprising a single service. A service can have 1 deployment or 2 deployments. So you will have deployment A or deployment B of the same service. So this is how things are segregated. So deployment A will have services A with pods in this domain, 10.10.10.1. This is some sort of gateway. The B deployment can have something completely different, 192, 168. So the deployments are completely isolated from each other. And there's ways how we can define these policies on a network level and also on a firewall level. If you're using Calico, that will be great because the BGP protocol allows you policy defining, but also you can have load balancer, you can have lots of ways, lots of abstraction layers of isolation. So in the control plane, the Kubernetes has the control manager and kube controller manager. Kube or QB, somebody's calling it QB, but I don't call it Cube. It reminds me of Kobe, so I'm quite sad he went away. So it's kind of like I'm calling it Kube controller manager. So the Kube controller manager has API server. This is like a connection point between the kubelet service and the kube proxy service. So the kube proxy service is running on the nodes, on the remote systems, machines, virtual machines, or whatever it is, servers. So in the kubelet and the kube proxy, you have communication that's scheduling stuff in the etcd, in the registry. So this is how the service discovery works. There is a health check performed, and these nodes that are containing all these pods and the containers inside the pods as well, the services, they can have some sort of health, and this is being reported to the kube controller manager. or Cloud Controller Manager, because the Kube Controller Manager runs on your personal host, but the Cloud Controller Manager is literally the same thing, but it runs in the cloud. So this is specially designed to run in clouds like Google Cloud Platform or Amazon WS or Microsoft Azure or OpenStack or literally anything. So that's a very good stuff, and this is getting upgraded as we go. And again, sure, if you need some more information, there is a link down. Just visit the official website. The documentation is immense. You can have a lot to read, and it's very interesting. They have a lot of information of this, and there are interactive tutorials which I'm going to show you later. You can try them before we start with some more complex deployments tomorrow. So the Kubernetes objects are a pod, a service, a volume, and a namespace. Just like in Docker, the namespace Kubernetes have namespaces in order to achieve isolation. The volumes are mapped in a similar way. You can use different types of file systems. I'm not going to mention all of them. I'll just give an example later of few. And you have pod, which can contain containers. And these containers can be grouped in a service. But there are also higher level abstractions that rely on something called controllers to build upon the basic objects. Because let's say you have a service. This service is comprised of different pods, but they will belong to one job. They will do one thing, and they will be one type of replica set. So this controller replica set, let's say, is going to be 2, and it's going to be for service A. So if you have replica set 3 for service B, it means that this controller will keep replication of one particular service at a time. And you will have controllers for different services. So all the pods and containers inside that are managed in this service, in this namespace, it will have specific replica set, specific number of replicas that it will be running. So this kind of controllers, they're managing all these abstractions. So I will explain about this more in later. This is the most difficult part, but trust me, guys, if you understand, this is going to be much easier. This is something that's I think the biggest caveat of Kubernetes and the complexity. But of course, there is the link here. You can visit. I'll provide this, of course, and you will just see what this does in detail. If what I said now is unclear. The pod is the basic execution unit of the application. It's the smallest and simplest unit, so you can deploy. So the pod will have a container inside, or a couple of containers, or 10 or 50 containers, and the pod will just be your process that you run in the cluster. So you type kubectl get pods, and you will get which pods are running in your cluster. Simple as that. And the service is an abstraction which defines a logical set of pods. So this is a bigger component. The service enables decoupling, because you can decouple different containers from the pods in different roles in the service and stuff like that. There is also volume level of abstraction and namespaces. So I'll talk about all these things later. Volumes are just like in Docker. The containers are ephemeral. So it means that if the container fails, data will be lost if it's restarted. So there has to be some sort of persistent storage. We will say that later. But first, namespaces. So there are lots of virtual clusters backed by a same physical cluster. So these clusters are called namespaces. They are intended for use in environments with many users spread across multiple teams. So you can have namespaces of, let's say, using Microsoft Office for developers, and using Microsoft Office for the testers and for whatever else. So that's just one way how you can put it. So you can put services in different namespaces, and of course they will have different pods, or you can connect these pods through specific service names in between different namespaces, if that means something for now. names of resources needs to be unique within namespaces, but not across namespaces. So if you put it in a one namespace, the resources inside the services, they have to have different name. But if you're talking about a different namespace, then the names do not matter anymore. There's other ways how you can connect this. There are control plane components. So first of all, we're going to talk about this. The control plane components are the main things that are defining the cluster in terms of the what's happening in the background, what's the machinery that's driving the whole thing. So these are detecting, responding to cluster events like starting new pods, replicas, how many containers are running, all these things that you don't really see all the time. The users are not aware of these. That's why they are called control plane, not user plane. First control plane element is the QB API server. The API server is it's exposing the Kubernetes API, and this is in front of the plane. So the API is connecting the QB API server with, if I go back to the slide, it's connecting the kubelet service and the kube proxy, which actually tells the API server, oh, this is a VM named this and with this IP address, and this is another one, and this is another one. So the API server serves to connect these things in between each other. Then you have etcd for service discovery. So this is a backing store, a key value store. So it's also a database, of course, and it makes sure that you have a backup plan for the data that fails. If something happens in the cluster in your high availability, then it will make sure that it will resume in the last state before it failed. Then you have the scheduler. The scheduler is observing for newly created pods, etc., etc. So another control plane components is the kube control manager, which is very important. The cloud controller manager is the same thing, except it's designed to work in the cloud. And this is a newer feature. So the control plane components, they are running controller processes, and they have something like node controller, replication controller, endpoints controller, and service account and token controllers. So these are required for your node to authenticate to the master, to the API server. So if you don't have, let's say, service account and token controllers, there is no way how you can exchange information between namespaces or between services. So this translates the same with the cloud controller manager, except it's a little bit different because cloud environments are a bit different than physical environments or bare metal. So next is, if we talked about control plane components, now we talk about node components. What's running on the node? The node is the actual host, the remote host. Let's call it a physical machine. It can be a VM, but it's in Kubernetes terms, it's called a node. So the node is running a kubelet service, and this kubelet is an agent, literally, just like the Puppet agent, something similar to this. So the kubelet agent, it makes sure that the containers are running in a pod. So if there is something going on, it will report to the API server, and we will know what's happening with the pods. Then you have the kube proxy. This is a networking proxy that allows the communication in the cluster. So the kube proxy maintains network rules on nodes. That's what it does. So it allows or disallows communication between pods or containers in the pods. You can apply filtering, packet filtering, and stuff like that. You can shape traffic, trigger ports. So this is the networking part. And then you have the container runtime. So the container runtime is responsible for running containers. Then you have Docker, Containerd, CRIO, you have Rocket, you have literally different types of container interfaces supported. That's why it's becoming very popular, because it's supporting literally everything possible. What's the cluster comprised of? So there is still more about this, but I will talk about something a bit more. Then we're gonna make a break. First, about the node itself. What is the node actually? In the language of Kubernetes, the node is called a worker. Before that, it was called a minion. If you've used Kubernetes before, now they call it worker. The worker node, also in the same language, let's call it language of Docker Swarm, it can be a physical instance or VM or a laptop or anything, or it can be some edge gateway or any kind of device on which you can run workloads. So each node, it will have the services to run the pods. So the node status is reported as follows. So first the addresses, which is the first important part, then the conditions, capacity and allocatable space, and you have information about the node. So this is going all from the operating system on the node through the container runtime Docker, which reports to the kubelet service, and through the networking, it's informing the API server what's happening inside the cluster. So the API server gets all the information necessary from all the nodes, and then the scheduler and controller manager can do according to what's in this information here. This is how things are done in Kubernetes. The node controller is a Kubernetes master component which manages various aspects of nodes, like the Puppet master in Puppet, something similar. One is assigning interdomain routing blocks, the IP addresses blocks. Then the other is keeping the node controller's internal list of nodes up to date with the cloud provider's list of available machines. So if this is running in a cloud environment, when a node is not healthy, the controller asks the cloud provider if the VM for that node is still available. So it communicates with the fabrics of the provider. Then the third is monitoring of health and other aspects. So you can have states like node ready or node status to condition unknown when a node becomes unreachable. So this is important before you run the cluster to know what's happening with your physical hardware. So if the pod is the basic execution in a cluster, it will be considered like a single process running in the cluster. So the pod represents a unit of deployment, a single instance of an application in Kubernetes, which might consist of either a single container or small number of containers that are tightly coupled and that share resources. You use mostly Docker in this to run these containers in the pods. And you can run either lots of containers or a single container in a pod. But most of the time you will run more containers in the pods, which will contain different aspects of your application. So one container can be Redis, the other container can be MySQL database, or there will be 3 different containers of the MySQL database, or it will be 3 same containers of the same database, like a backup or a replica to increase performance. So if you're doing something like that, most of the time inside the pod, you will have one container of database here, database 1, one here, database 2, and database 3. And then you can load balance between these 3 databases, depends on the requests coming from the outside. This is something Kubernetes does by default, out of the box. You don't have to configure it, but also there is ways you can configure that to use different load balancing algorithms, like we mentioned before. So that's one way you can do this. You can run, let's say, that's going to make a high availability database. If one of the pods fails, it will rerun it again anyways. But let's say the node fails, the hardware burns down, or the RAM chip dies, or the CPU dies, you will still have 2 databases running. And the etcd, the outside key value store, will make sure that the databases have the latest information possible, so the failure of this database is not going to cause some substantial problem in your application state. So the workloads, the pods per se, they can have something like I mentioned before, one container. It can have a container and a volume. It can have two containers sharing the same volume, or it can have one container with one volume or another container with another volume. So there's lots of combinations you can do this. Each pod has a different IP address, and they're usually connected in the same subnet unless pointed otherwise. For more information on this, you can also visit the website. I provide all these links down below, and you can just check in a bigger detail about this. So I'm not going to be able to mention everything now. So how the pods manage containers? They use networks and storage volumes, like we mentioned before, and they're supported. They're designed to do stuff like this. So the grouping of multiple collocated containers is advanced use case. Then you have something called, I think it was, let me check if this is in the next slides. Okay, we're going to talk about this. You have something called like controllers, which act in the pod for different purposes. But the most common types of communication is network and storage. So it means that that's how things are shared between each other, the information between the containers in the pods. But the controllers, they're doing something else. The controller can create and manage multiple pods. So they are handling a lot of stuff, including replication, rollout, providing self-healing capabilities in the cluster, or like I mentioned before, if the node fails, the controller can automatically replace a pod. Okay, I see. Yeah, I understand that it's a big topic. Somebody is having difficulty because the presentation is long, but I mentioned that we are going to separate this into a couple of ways. So today we're not going to do the practical part of Kubernetes. I know it's difficult to concentrate, but I'm going to have to go through the stuff that are necessary to proceed. Otherwise, it will be very, very difficult to do this in one or two classes. This is a thing that's usually done in multiple. But for the basic stuff, you can do a lot. And I will provide these slides for you, so no worries. And this will be recorded. If you miss something, in case you have attention deficit or anything else, you can always replay the videos and get more information. So I believe that we can also make one more break after this, after I explain the pods, and we'll continue, because we have also like around 30 to 40 slides. So I'm not going to go through all of this, of course. I have some examples which I share with you in case you start to do load balancing and things. So these are just for your convenience. So I'm not going through the code, but I have to finish with the architecture, which is just a few more slides. No worries. Okay, we can take a break after this slide. Just let me finish with this one, and later there is also some interesting stuff. I will talk about the networking, virtual IPs, load balancing, how you can do this, and I provided some code for you so you can have stuff to do for the project, so you can use it literally copy paste. But yeah, later we will have some Docker practical part, and tomorrow we will do the Kubernetes part because it will be too much for one day. So half an hour, 40 minutes more maximum. So about the pods and controllers, this is something best explainable in practice, but you need to know just the most important parts. What is a deployment, what is a stateful set, and what is daemon set. I will talk about this later. What is deployments, daemon set, and stateful sets. So this is the most important thing for you to understand. After this, it will be very, very easy to deploy clusters and work basic stuff. But Kubernetes is a very big topic. So if you go to the official website here, you will find that it's a very, very extensive system and it's super complicated. So yeah, I suggest that we take 20 minutes break now, something around 11:50, and we'll come back. I will continue with some examples so you can see. We're not going to type anything now, but I will provide this for you because these are copy paste text, so you can use it. All of this is from the official documentation, so it's something that works. Yeah, so I think 11:50 is quite enough. I'll be back here so we can proceed. Okay, so we can proceed with the examples. Let me just put this in full screen. Right, so this is a small example of a template that prints a message. So this is how you can run literally an app with Kubernetes. So it will pull a small image, which is, I think, the smallest instance you can get, called BusyBox. And this will print a message. So it will say, hello, Kubernetes, and run it in a pod. So it will run as an app. It will label it as my app. So you can put any name as a label you want. And when you put kubectl apply, it will run it as a single pod. The thing is that as you can see, this kind of declarative way of expressing things is very similar to the one in Docker Compose, because they're using YAML both. Another example to run Nginx web server is, as you can see on the left here. So this will run Nginx, but let's talk first how this is run, because what's the difference between this and this? This will just run a pod and that's it. But in this case, we're creating something called a deployment, and the deployment can have multiple replicas. It can be put as a template, and it can have specification, which will be containers and the name of the image from which you're going to run the container. So the deployment provides declarative updates for pods and replica sets. So you describe the state that you want in the deployment, and the controller, the deployment controller, changes the actual state to the desired state. So later you can update this. Let's say you run this now and you want to update to 4 replicas. You just change it 4 in the file and you apply, and it will update, and that's it. That's how simple it is. So this is one example how you can do it, but it's just for the matter of explaining the deployment as a concept. Then you have something called daemon set. Daemon set is a literally set of daemons that runs on the nodes, and it's a small copy of a pod which is making sure that the nodes are running. So this is taking information from the nodes, and as you add more nodes to the cluster, the pods are being added to them, and the daemon set will make sure that these are registered. So if you add more VMs, you can register all these VMs in your cluster. So this is done through the daemon set. Their typical uses, this is just some examples, running a cluster storage daemon. So you can use Ceph. I can show you this in 3 weeks when we start learning about Ceph storage. And running logs collection daemon or node monitoring daemon. I will show you later how you can run the whole Elastic Stack with just one command. So you can collect logs, you can monitor logs with Prometheus. There's endless ways you can do that. You just don't need to use the node exporter from Prometheus, which will take information from the nodes, but you can use Flowmill, you can use sysdig agent, collectd, Dynatrace, or anything. So there is this elastic metric beat. It's similar to Prometheus node exporter. It works in the same way. Everything works with Kubernetes. So this is the beauty of the system. If you want to run a daemon set, you can just run it in a file, or this file is taken as an example from the Google repository. For the record, Kubernetes is invented by people from Google, so now and then it's sourced, it's open sourced, and the thing is that they don't own it anymore, so it's an open source community. It's a huge community, and now they have their own community, so it's a very big thing, so it's a big deal. And as you can see, some of the repositories they store still in the Google, so the images you can pull are from there. Although you can do private repositories or Docker or any other cloud location or Artifactory or whatever you want to achieve. There's a lot of ways. So, for example, this will run a fluentd Elasticsearch Docker image. What does this do? So when you put the daemon set, it will put the daemon set in a specific system. So the daemon set will have a name fluentd Elasticsearch, which will designate that you're running something, so you can identify your daemon set. This is just a matter of metadata for your daemon set. Then you add the specs. So in the specs, you're adding what's going to be run inside. So you will have a selector, you will have a template, and the template will have some specs. So the selector is just for managing the information that's put in this name. And the template will be actually what you're going to put there. So you're going to put the key, let's say. The node role, Kubernetes master effect, no schedule containers, which containers, how much limits to the containers, megabytes in memories, how much for requests, 100 megabytes in CPU in memory, so you can limit the request rate per container. Then you can use volume mounts and etc. So in the end, what I did, sorry about that. I think it was this one, yeah. In the name, you just put var log and you put it in this host path for the volume, and inside the container, the varlib Docker containers. But the thing is that this will run an image, pulling a ready image from the repository. It will be version 2.5.2. Maybe there is a newer version. You can adjust this according to what you need. Or there is another way. You don't have to have this file in your host to run it. You can just use kubectl apply -f and provide a link to this file. And this is a place where I took the file from. So you can actually use the same command to run the fluentd Elastic Docker image through this link. Then we talked about daemon sets. Now stateful sets. What are stateful sets? They are workloads, API objects used to manage stateful applications that keep states, like deployments and scaling sets of pods. It provides guarantees about the ordering and uniqueness of these pods. So there are stuff like, for example, number of containers that run in a pod. So if you want that number to be exact all the time, the stateful set will make sure that that number is as you want it to be. So if the pods are created from the same spec, but are not interchangeable, each has a persistent identifier that it maintains across any rescheduling, like in the previous example. So in the spec, you're having a selector and labels of each spec. So in stateful sets, you actually the stateful sets are managing the deployment and scaling of set of pods, and it provides guarantees about the ordering and uniqueness of these pods. It's similar to deployment, except the stateful sets manages pods that are based on an identical container spec. So this spec, you just put as a template, or you put it as you can assign everything here manually. So for example, in a spec, you can put that the termination grace period of the container will be 10 seconds, and the containers that are going to be used will be from this image, from this link, and it will expose these ports, etc., etc. So those are specs. The stateful sets are for example, valuable for applications that require some stuff like this: stable, unique network identifiers, persistent storage, graceful deployment and scaling, or automated rolling updates. So this is very good. It's kind of difficult to explain like this, but I will try to explain it next time when we do practical in a practical way. So I'll try to cover all these things in a practical manner, because it's you first need to understand what it does. If I talk about them in a practical way, then you will don't know what is stateful set. So unfortunately, we have to go through all of this before we jump into the practical part. And on the side, you have examples. So later we will talk about replica sets. So this will define how many replicas you will have from pods running at a given time. So usually you want 3 replicas at least, or 4, to have some sort of high availability, and most likely this to be deployed through different nodes. So if you have different nodes with different IPs, different physical machines, this will be deployed through different nodes, and you will have high availability by default. But in order to have that, you need to have load balancing, service discovery. You need to have some sort of state persistence, like with etcd, and reverse proxy, SSL termination, all these things all together. So this looks simple, but it's not quite. So to get to this part, you need to pass a lot of path. The link a replica set to its pods is via metadata owner reference field, but the replica set identifies the pods by using the selector. So the selector that we have defined previously, for example, this one. So this is how the replica set will know about the name of the specific pod. So you can do this command, kubectl get rs, which is for replica sets, to check the replica sets. To pull this code, also you can apply -f the link from where this example is taken from. So this will run PHP Redis containers, like a front-end application. So that's just a small example about this type of deployment, which is replica set. So there are also jobs. To defer these, the jobs create 1 or more pods and ensure that a specific number of them successfully terminate, actually. As pods complete, the job tracks the successful completions, because a pod is not an eternal entity. The pod is meant to die. So the pods get killed because of various reasons. They have a specific execution potential, time, overwhelming, or what it can be any kind of reason. So the pods are known to be temporary, and the jobs are making sure that this is known, and this is done in a clean way. So it's more or less like the hitman in Kubernetes. So it knows that deleting a job will clean up the pods it created. So it's the one who tracks the stuff and makes sure things are executed in a proper manner, as well as deleted and done. So this is tracking literally of the stuff happening in the whole thing. So the jobs need API version as well. The configuration is similar like with the other things. Then you can assign metadata, names, PI, job, whatever it is, and you can have specs as well, a template for the specs, a container that's like Perl, some Perl image, and it will run at some specific command. So you use this. I'm not sure what it's going to do in Perl. It's not my field of expertise, but in any case, that's how you can do jobs, and you can check them, for example, with kubectl describe jobs and the name that you specified in the metadata. So there's ways how you can assign jobs as well. Now I'll talk a little bit about services, load balancing, and also networking, because these usually go together. Like we talked about Docker and load balancing before, if you remember. In order to achieve specific connection load balancing between pods and containers, you need to have a specified set of network endpoints. So these endpoints are referred to as endpoint slices. So endpoint slices are groups. They are groups of network endpoints, and they're grouped by unique service and port combinations. So you need port, you need IP address, and the typical things in order to have a connection. So the thing is that you need also to specify if you're going to use IPv4 or IPv6, or you can use both. There is dual stack option, something like that. So the Kubernetes can work with host names. It can work with zones, regions if you're using if you're using it in a cloud environment, etc. So this topology, for example, labels, they will be set by the endpoint slice controller. And the values of these labels are derived from resources associated with each endpoint in a slice. So that's how containers identify with each other using host names and DNS. So this is mostly done with conjunction with addressing and advanced routing in SDN, because only using DNS can represent a problem, and DNS spoofing can become a liability eventually. So there are ways how this is being secured and tackled. So service is, I think, the most important part to remember. In Kubernetes, a service is an abstraction which defines a logical set of pods and the policy by which to access them. Sometimes this pattern is called a microservice. The set of pods targeted by service is usually determined by a selector. So this is how you define a service. It's just a small example. You put kind to be service, not daemon set or replica set, and you just put a selector my app to name it, and you put ports, this port and this port. The service will have this port. So whatever you run inside this service, is it going to be a web server, it will be assigned specific ports. So the IP address will not be relevant. So when you're accessing on port 80 on the main machine, it will translate it to 9376, and it will just access that all the pods that are running in that service namespace. So this is how things are being done. A service is a REST object. This is also one way to describe it. It's a similar to pod, and it can have it can post a service definition to the API server to create a new instance. So we will see something about this. It's a good example to try later in practice. So this is an explanation what this does. So the specification creates a new service object named MyService, which targets TCP port 9376 on any pod within the my app label. So all the pods that are be running inside that service, they will have the same ports and probably different IPs. So depends how you define these things. So the controller for the service selector continuously scans for pods that match its selector, and then it adds all these attributes to these pods. Then you have virtual IPs and service proxy support. This, I think we all know what this is. By default, the Kube proxy in user space mode chooses a backend via round-robin algorithm. This we choose to round it to run it in a user space mode. So in the backend, you will have like proxying in round robin, like I explained the load balancing earlier with Nginx. If you don't do anything in configuration, by default, it will do round robin. So there is another way, so you can proxy using IP tables mode. So this is more or less different, because then you assign forwarding rules to different backend pods. So if the Kube proxy is running the IP tables mode, the pod that is selected doesn't respond, then the connection fails. And this is different from the user space mode, because the Kube proxy selects that the connection to the first pod failed, and then automatically tries it with another pod, with the next one. So this is also one way to do it. And I think the best way to do it is by using IPVS proxy mode. It will offer you the best performance available, because in IPVS mode, the kube proxy is watching Kubernetes services and endpoints calls netlink interface to create IPVS rules accordingly and synchronizes IPVS rules with Kubernetes services and endpoints periodically. So this control loop ensures that IPVS status matches the desired state. When accessing a service, the IPVS directs traffic to one of the backend pods. So yeah, there are lots of ways that we can configure this. Round robin is by default, and most likely will not touch this because this is the default state that it works in. But you can change it to list connection, to destination hashing, source hashing, shortest expected delay, never queue algorithm, and you can really try. And I think IPVS will offer you the best performance. So ingress and egress controllers. So this is a mistake here. I'll correct this. So you can deploy ingress controllers also with Nginx. I will show you how to do this. We can have SSL TLS termination point. And also we can set up a load balancer. We can set up a reverse proxy and everything in a similar manner. So I will try to do this for you with Docker manually so you can see what it does and how it's done. And then you can do the same with Kubernetes by deploying the whole thing automatically later. So this is, I think, the basic approach, more or less. To define ingress, you need HTTP and HTTPS. You can generate certificates manually, but it's not gonna have any difference. I think the best way is to use certbot. So, right, I think that I'm not gonna be able to do that because I don't have any domain name at the moment to show you directly this, but I will show you how it's done. So in case you want to do HTTPS termination, that's quite straightforward if you're doing it the right way. But there's lots of shades. So to provide ingress resource in Kubernetes, this is actually basic because it has to have some sort of ingress. The HTTP rule has to have a path, and the path has to show to some backend. So this backend is your pods that are running in your backend of the application that is being served. So if it's a web server, the traffic that's being sent to these backend pods is going to be load balanced in round robin, and it's going to be terminated to HTTPS if you specify that later. But in this case, it's just an HTTP flag. So there is single service ingress, and there is also a simple fan-out ingress, and there is name-based virtual hosting. So there's different types you're gonna do this. Single service ingress is not a common thing. So it will allow you to expose a single service, and you can do this with an ingress by specifying default backend with no rules. So the ingress controllers and load balancers, they can take a minute to allocate the IP. So this is how it's done, and most likely will not do this. The most common way things are being done is with a simple fan out. This is just a primitive example, but this is something that's been done. In fact, you will have a couple of services in the backend. So service 1 with port 4200, then you will have service 2 with port 8080. So they will be hosted in a single host, and access to them will be through HTTP. So if you go kubectl describe ingress simple fan out example, as we name it, because you have to put a name through it so you can actually access to it. So there is another way you can describe these things. If you don't have a specific name, it will give you something like this. So the simple example, the namespace is default. If you don't specify it otherwise, then it will put everything in the same default namespace, and it will add some address there, the public address, and the backend it will put randomly, or it will put it as much as you specified. In this case, you didn't specify any kind of subnetwork, so it will put everything randomly by order. So in this case, you will get the Nginx ingress fan out, just like it shows in this site, that the service 1 is exposed on port 4200 on this IP and service 2 on this IP. So this is how you load balance, and the traffic coming from the main IP address, it's going to be round robin through these two addresses. You can use a different algorithm from one of those from before if that works for your application. Then you have name-based virtual hosting. You can also redirect via names. So you can use DNS entries, or you can specify names for the service. So everything coming from outside to this IP address is a HTTP request, either with two options. It will just be redirected to the same IP address to a different service. So I think you see how this goes. It's quite simple, and yeah, this is also a way to host a couple of different websites on the same IP address. Let's say it's a very good thing. So you can reuse the same VM, and the hosting you pay for, it's gonna pay off for you finally. So it can be an interesting thing to achieve stuff. Then you have another way to do this. You can specify the name, the virtual host ingress, so you can access it later. And then you specify the specs and the rules. So the host is going to be, one of the hosts is going to be foo.bar.com and bar.foo.com. So you have two websites. They're all listening to port 80. So you don't have to use different ports. Otherwise, this would be impossible to do. So you see where it goes. So if you have one service and second service, you have two different websites running on the same IP address on port 80 both. So that's amazing. You just use a different name to distinguish between them. If the name foobaris.com is requested, then it accesses the first website. Otherwise, it will access the second website. So this is how ingress works. And this is usually done with Nginx. There's other applications. I will show you a couple of examples also with Docker, and I will give you a document for this in a PDF form so you can try it yourself. Right, so you can add more. I think you can add service 3, you can add service 4, etc. So yeah. Then you can terminate TLS and SSL, and yeah, you can secure the ingress by specifying certificates, and these certificates can be put through a specific fully qualified domain. So you have to expose, in that case, port 443, and you have to define where your certificate is. So this is something we're gonna do in Docker, so you can see how it works. And then we can try the same in Kubernetes to deploy the same things that we do in Docker with Kubernetes, and plus some other stuff like monitoring. I will also give an example how you can deploy the Elastic Stack with Kubernetes. So it's a very convenient thing. The further is policies, network policies. In the network policy, there is a specification about what things can communicate with what. So in that case, you put egress and ingress policies. So in ingress policies is what can be accessed from where inside your backend. So it means that you put IP blocks from this to this, or from, you have a from to, like for example, from this source, they no, actually, in the case of ingress, everything that's coming from the outside in the IP block, the namespace selector is gonna be actually what you're gonna put in the actual policy. So everything is being identified by your names that you put. The IP addressing actually does the isolation of pods, and this is something that you do to select these pods. And once this network policy, there should be a network policy type, so you can put ingress or egress. Once this is in action, the pods will actually be isolated. So the network policies, they do not conflict, they're just additive. If any policy or policies select a pod, the pod is restricted to what is allowed by the union of those policies, ingress, egress rules. So the order doesn't really matter. So in case if you have actually IP block like this in egress and ports like this, everything coming from outside through your front end, it will just access to these specific ports that are specified in the backend. So in this case, you have a pod selector that's specifying front end role and for the specific project. And this will just add that everything is accessible to this except not this. So you can do filtering like this, network related. Policies can have different types of shades, and you can use these flags. I provided this so you can have an insight. If you want to use them, you can try this to secure your pods. It's also adding a layer of security, but there's a lot of default policies, and you can find them on this link. So you can have IPv4, IPv6 dual stack, which I mentioned before. So it means that you can put either this, or you can use both in order to provide networking inside your backend. So the service can have IPv4 and 6. So that's something that you can do. The kubelet proxy will just do this. If you assign proxy mode IPVS, which is quite suggested, then you will have both dual stack networking. If you specify IPv6 address block larger than 24 via cluster interdomain routing addressing on the command line, that's not going to work. If it's specified in the file, it will make it work. But if you do it through the command line, because all these commands you can also do through the command line, if you specify the IPv6 through the command line, that's going to fail. About storage shortly. The storage, just like in Docker, it's ephemeral, so you have to make sure that that you have some sort of persistence. When you restart some containers, it can fail. Luckily in Kubernetes we have etcd, so at least until hosts and physical machines are running, this will be still on. The difference between Kubernetes and Docker is that also Docker, that it has this concept of volumes. It's not as managed as in Kubernetes. In Docker, the lifetimes are not managed, and they're just local disk volumes. So when you specify a volume, it's something that's short-lived locally. Now, as of new, Docker provides volume drivers for the storage, but I'm not sure if there is something called the CSI, Container Storage Interface. I'm not sure if that works very well. So this is quite a new thing, but Kubernetes supports many types of volumes, and the pod can use any number of them simultaneously. So you can use Ceph FS with Gluster FS with it's amazing thing to do. So yeah, if a pod ceases to exist, the volume will cease to exist too. But if you use persistent storage, then that's not the case. So that's the difference. There are ways how we can implement these volumes. So, for example, in Cinder, this is the volume manager of OpenStack. If you want to integrate to manage the OpenStack storage through Kubernetes, you can do it like this. So this is just some test volume, and it runs through Cinder service, and it will assign volume ID fs type x4, and it will just assign a volume in OpenStack. So if you're managing OpenStack with Kubernetes, this is the way it's done. Then you have Ceph. Ceph is a bit different way things are done. You can use secret files. You can put it to be read-only, etc. So that's another example, but in practice, I think we'll talk about Gluster FS or Storage FS, because these are a bit more simple and they're similar. So Gluster FS is a bit similar to Ceph, but still these are like the most common things that you will experience. More information on this you can find in the link here. So this is also quite an extensive topic to talk about the storage. And security shortly. So security is inherited. So it means that your container is be as secure as your cluster. So if your cluster is not secure, your containers are not going to be secure. So if your cloud data center or whatever location is not secure, your cluster is not going to be secure. So Kubernetes by default is not secure. It can help increase security if you know how, but if the security fails at a different level, then that's going to be very tricky to achieve. So if you really wish to proceed with a secure infrastructure, you need to make sure that the deployments you're achieving through Kubernetes and Docker are put on a secure place. Cloud is a somewhat secure place, depends. But when you have multi-tenancy, you're sharing resources such as CPU, RAM, memory locations. So this can be tricky when it comes to exploits on a hardware level and on a lower level. So nothing that you put in this security is going to work. So there is something called cloud native security. It encompasses best practices how to achieve this, and these are sublimed in the following tables. So one of them is using role-based access control. So authorization of roles, who is going to access what and be what kind of role in the cluster, and more information about this on the corresponding links. These are very big topics. And if you're interested in security, there is definitely a lot to talk about. TLS for ingress, this is something I will cover. Network policies, there is, I think, some small information about this. So quality of service, pod security, there is literally a lot. And then you have also container level security, if you want to talk about that. Container vulnerability scanning, which is enterprise level feature of Docker mostly. Image signing and enforcement. So this disallow privileged users, stuff like that. So there is a lot to talk about security, and we don't have time, unfortunately, for all of that. But I have provided some reference here, so you can check it out if you want. Policies are simple. You can limit ranges, or you can use resource quotas. So these are more or less to define how much of a resource your container is going to use. So you just put small block resources, and for requests you can put how much memory and CPU to assign. Then you can put limits like 200 maximum and CPU 500 maximum. So it's like it's gonna be the maximum that's gonna be for this container. Then you can put different names of images. So BusyBox CNT02, CNT03, CNT01. So you will have 3 different containers running there, and no, 4 actually. So they will just do hello from, so they will just print a message each from each other, and they will have some specific limited amount of resources to run from. Yeah, so this is a small example. For limiting ranges, you can literally do a lot of things, and you can check it here on this link as well, how to define these policies. Although you can put an example like this to try it, and you can create it with kubectl create namespace limit range demo, and then kubectl config set context, and in the current namespace limit range demo. So to avoid passing the target limitation demo in your kubectl commands, you can change your context like this. So yeah, this is a very small example. Then you can use also resource quotas. So this is when you're having different users and teams, they will share a cluster with a fixed number of nodes, so you can share the resources between them. Last but not least, I will introduce Helm also. We will install Helm, and I will show you how to use Helm, because Helm is a package manager for Kubernetes. And the Helm is actually working with charts, and it has configurations. So the charts are like more or less like Puppet manifests. They're like the Linux packages. So you just install and you're ready to go. You can create your own, and you can push them to your repositories. So you're just ready to go with out of the box applications. This is very good, and literally it will help you to stop copy pasting stuff. So yeah, next is a practical demo and some exercises. We're gonna get some break before that, of course. You have some information to read if you want in these 2 links here. So before that, yeah, little break, nothing else. I'll come back around 1 o'clock, and we can start. So I will talk about Docker. So we will do some examples in Docker. In the meantime, you can install it if you don't have already, if you haven't tried it. I put also the exercises in the Trello boards. But if you haven't done that, I'll find you the slide so you can do the installation of Docker on your system. So we can try some stuff. I can show you some basic things and also a bit more advanced stuff. We will do some reverse proxy load balancers and SSL termination. So yeah, I will share in the meantime a configuration file for Nginx on the canvas. And so you can have the commands, but I think we'll type this one by one so you can know what's going on there. All right, so around 1 o'clock, I'll be back. I will resume recording now. Right, so the Docker command line is issued all with the Docker commands. So to see all of them, you can just type docker ---- help, and it will show you all the possibilities you have. You can use -d to debug stuff. And most often you will just manage images, networks. You will manage nodes if you're running in Swarm, like in microservices. You will manage plugins, network plugins, and all of that. We are not going to cover all of this because this can also get too much. So I will just keep it simple for you to understand what it can do. In any case, if you want to go further, I will provide some examples for you in PDF so you can try these things by yourselves, deploying web servers, deploying some stuff, and it's quite simple and straightforward once you know the procedure. So there's lots of commands you can issue on containers and services. So you can issue attach, build to build the image from a Docker file. So you need to create a Docker file. There are slides posted in Canvas from Kira. It shows you the basics of Docker file. So I don't have to go through this and we can focus on the command directly. You can also work with images. This is also important command. So you can see all the images you have in the system. So if you type Docker images, then you will see all the images that are pulled here. So I have some Mongo database. I have, there's the 5G network core that's running. So this is 11 gigabytes, quite a big image. Then you have some Nginx proxy and Nginx web server. So the images usually are grouped in tags, and these tags shows the version of the image. So the image will be latest if it's the latest tag pulled from the repository. So in this case, I have my own private repository and I'm pulling my Nginx web server image from there. I can remove images, for example, Docker RMI, and you can use a name or you can use the image ID. So I can copy paste this ID here, or I can use the name to remove it. Like you just type the first couple of letters and it will go further on. So Nginx. So this will remove the image. What? Some mistake somewhere. Yeah. Web server. There it goes. So it will remove the image. Everything that's related to the image will be removed. It removes the SHA hash and everything. We can remove image by RMI, which stands for remove image, by the ID. So if we copy paste the ID, it will also remove the image by the ID. So if I do Docker images, I will not have anymore these images that were there. This is the Rocket chat. I was preparing to make this work. I didn't have enough time, but we still use Zoom. In any case, you can deploy Rocket chat in Docker and Kubernetes with just a short time, and it will be up and running in no time. So that's the beauty of this stuff. So if I want to pull an image from a repository, you need to get a grasp on the Docker Hub. So I will just go to the Docker Hub so you can see what I have there. Let me share the screen with you. So this is the screen, I guess. right? I hope you can see the whole screen now. So if I go with my ID in Docker and I sign in, I'll go to the Docker Hub. So in the Docker Hub, you have images that you can push from here. So to log in there, you can use Docker login. After you create an account here, so it will request your username and password. It says your password will be stored unencrypted in log. Oh, that's very great. Thank you. So that's awesome. Nevertheless, when you log into your repositories, you'll have your stuff that you push there. So most of these are public anyway, so anybody can download this. Even you can download them. So that's how you're gonna use these. So the Nginx proxy and the Nginx web server is out of the box image. So this is not changed. This is not configured. All the configuration you can do on your local host, and I will show you how with the configuration file. So the only thing you can do is you can pull these images to your host. So you can do docker pull my name and surname / Nginx web server using default tag latest, or you can put semicolon at the end of web server and use tag version, I don't know, 1.4 or something, but I don't have anything like that. Docker offers you version control, so you can have rollbacks in case something goes wrong. In case something goes wrong, in my case, I just delete the web server and I run it again. So that's not a problem. Then you pull out also the other image, Nginx, I think it was proxy, if I'm not mistaken. Yeah, so if you copy paste this name, or if you click on it, it has some explanation I wrote here. It's a simple container that terminates SSL and proxies traffic to inner servers from port 443 to 8181 on the given IP address. So yeah, if you want to put a configuration file, you can put it somewhere in a directory here and just add -v. So this is how you can run this container. I will show this later, but when you enter this small piece of information here, it will show you what you can do with this. And usually it allows you to copy paste this command, docker push, so you can push a new version there. And that's how it looks. So I can pull this. It's pulling the latest image. So this is how fast it works. It doesn't require any installation because the image is already installed inside the container. You can do this by manual installation using Docker file. You can install Nginx with Docker file, but you don't have to do this right now. In the other slides from Kira, you have detailed explanation on working with the Docker file. So to make it simpler, let's try to run the web server. So what I can do is like to run the web server, I can type not Docker, Docker run minus interactive mode and daemonized mode, let's say, and I can put a name to the container, minus name, or just a space. I think it can be put also minus name, if I'm not wrong. Let's put it Nginx1, and yeah, let's assign a folder which we're gonna serve. So we're gonna serve a folder named -v root, and let's name the folder docker nginx HTML. So this is gonna be your local folder where you're gonna store your local files. So in root docker nginx HTML, you put your website. And this website is gonna translate after the semicolon in the container in user share nginx HTML. So this is the directory where Docker is containing the Nginx web server inside the container. Pardon. And in the end, if you want to run just Nginx, if you do this, it will pull Nginx web server from the official repository from Docker and run the out-of-the-box Nginx web server Docker image. But if you run my image, I think it's just going to be the same, except it's going to be a little bit outdated because I haven't updated it inside the container. So it's going to be some older version of Nginx. Nginx web server. And if I press enter, there is some mistake somewhere. Unknown shorthand flag and in a name, right? So it will allow you to, yes, pardon, I will put it in full screen. I will add the name with just this, minus name, and I will pull equals. So when you run this, the container will run. And if I check this, you will have the name of the container that you put. By default, port 80. So it's running. So it's up 3 seconds. If you type the command again, up 18 seconds, it means it's not quitting. To stop a container, you can do, you have to actually do docker stop nginx1. And you can also add docker remove nginx1. That's the right way to do this. The wrong way is docker stop -f nginx1. If you're doing forceful remove, then you're doing something wrong. So the right way is the above way. There's another way how we can remove all the containers. It allows you to do something like this: docker stop docker ps -aq. So what this does is it pipes in a command ps, which is listing all the containers and formatting them only by the ID. So the ID of the container, which is this one, will be listed, and all of these containers with this ID will be stopped. And you can also do the same with, pardon, and also the same command, but with remove. Docker remove -aq. And this will stop and remove all the containers that are running. Shorten flag AQ. Okay, let's see what's the problem here. Let's check first if it's gonna, yeah, okay. It should be fine. Docker ps -aq and docker remove -aq. No. Yeah, that's, I'll try to type it again. Docker stop and okay, one by one. Docker ps -aq, and this should pipe it in. You see, it stops the whole thing, and now the containers are stopped. If I list all the containers, which is only one in this case, docker ps -a, it will say that the container is exited. And now if I type docker remove and the same way, it will remove the container. So you can do this in one line. There, yeah, it requires only one end probably. So I just missed this. Right, so you can just do this. This is the right way to do it. Never use forceful. If you use forceful, then something is wrong. You can use it if something doesn't want to stop and remove by default. Now, another way, yeah, somebody mentioned, yeah, you can use docker system prune --all to remove dangling images and stop containers. Very useful in dev situations. Depends. Sometimes if you want to remove everything. So there's lots of ways you can do this. There's not really right or wrong way, just whatever way suits you. So if we want to proceed with the web server, I'm going to go back to the command for running the server. So what we missed, what we can add here actually is IP address. We can add also a lot of stuff. So first thing is we can add ports -p 80, 80, or you can add -p 28764, whatever, 763, 80. So the port 80 will be exposed on the container, while this port will be exposed on the host. So when you're accessing the web server from outside on this port, it will always go on this actual port inside the container. So if you do this, you will just trigger port 80 to port 80 in the container from outside. So if you do this, then the container will be accessible from outside on your public IP address in the instance. Yeah, there is, it's showing that forbidden because I don't have anything at the moment inside the container running. I mean, inside the directory, because if I want to serve a directory, I need to go to Docker nginx HTML, and here you need to put some HTML file. So I don't know, we can just add some random HTML file. I forgot how it was. HTML, open one, and I think close one. And we can add heading or something like that. I think it was H Docker nginx, and then we can close the heading. Let's hope this thing works. We need to restart. So now if you go to the website, I'm not sure it's gonna give you any difference. You need to restart this. So in order to restart, you need to just restart the container. So docker ps -a or whatever. You can see the ports are exposed on the public IP, and you just do docker restart nginx1. If you don't have any persistent storage, that's gonna go to hell inside the container. So we are using local volumes to solve this temporarily. So if we check the container again, it's up 8 seconds, it's restarted. So now there should be something, given that everything works properly. 403 forbidden, there might be some sort of blocking of some traffic, or there is still some sort of caching involved. Nevertheless, that's how this is done, but we're going to go with some better example now. This is just basic. So we're going to stop this, docker stop. Let's put the command from before to stop all, docker ps -aq, and docker remove docker ps -aq. Yeah, right. Whoa. Something's going on. It says error response from daemon. You cannot remove a running container. Well, we can check what's going on. It's removed. Okay, well, that escalated somehow. Things like this happen. But you can always remove forcefully. It's not recommended, but in cases if something doesn't go, you can just rm-f. Another thing to consider now is working with the networks. So in Docker, you can actually list the networks, docker network ls, and it will show all the networks that are running around. So you see, I have some network named root default, some network net A. These are added additionally. the default networks that you will have is going to be bridge, host, and none. So these are available, and you can run containers and attach them to these networks. Given that these networks are attachable, there is an attribute of a network attachable. So to check a network, you go docker inspect network and name of the network bridge. It should give some attributes for this network. Take some time, but fine. So it tells that the bridge is it has ID. It's created sometime, wherever it is for restarting the daemon last time. So it has subnet and gateway. And this is more or less how it's done with the bridging, because the bridging uses VXLAN to bridge between the main interface and the Docker 0 interface. If you go to if config, you will see that Docker creates a Docker 0 interface by default. So this is the interface through which the Docker containers communicate with the physical interface. So these are two bridged. If you ping between these two, you will receive response. So this is the OpenStack, and this is the Docker. These are some additional bridges created by Docker 1820. So this is added as the networks are being added. This is some VPN thing. It's irrelevant tunnels for 5G, so we don't talk about it. So if we check the networks again, Docker networks, Docker network ls, we have some additional networks. That's in my case, you will have only 3. I'll delete these for the matter of convenience. Docker network RM, just like removing a container. You can do it by the name or by the ID. So let's use name, net A. It removed the network net A, and you can also Docker remove Docker network remove, and you can use also the ID of the network. It will remove both networks. If I list the networks, they're gone. So these are the default networks that come with installation. All right, so what we're gonna do now, we're gonna create a network. I'll just recreate the same network, and we will attach some containers to that network. Docker network create -d, which is the driver. So here now you have option. If you type --help, I hope it will show you what options you have. Not quite. In the documentation of Docker, there is literally a lot of description for this. You can use overlay if you're using clusters, bridge, like by default, you can use Mac VLAN, IP VLAN, a lot of stuff. And if you have third-party plugins, you can assign these. So for example, we can use what's coming out of the box. Docker network create -d bridge. We'll use the bridge. If you're running it in a local PC, you can use Mac VLAN, and your container becomes part of the subnet of the physical network. And then we can define subnet. So we're gonna add subnet to be 172.18.00.24 or 16, if you will. So you will use the both address ranges, so you can have a lot of containers. And then we will just add a gateway. Otherwise, it's not going to work. In the gateway, you can put 172.18.01 most often, according to the CIDR routing. So you can, if you use some other mask, then you're gonna have to change the gateway accordingly. Attachable and net A, let's call it net A, like it was before. So this is gonna create a network in the bridge driver and use these parameters for subnetting, and it will say that the network is attachable. It means that you can attach containers to it. So now it creates a network. Okay, if you remove -d before help, shows option. Docker network create -- help. Right, you can have some settings, IPAM drivers, but out of the box, it's not going to show you which drivers you're going to have. My point was to check which drivers you can use. But when you use -d, you're going to have to use driver, and then you're going to have to use something. I'm not sure if it only offers bridge overlay and some stuff. Like there's a lot of things you can use here, and they are not out of the box. Nevertheless, now we created the network. So if you go Docker network ls, we have the network here. If you can check the network, Docker network inspect. This is very useful to see the parameters of the network quickly, so you can know which addressing to add. So these are the most common commands. Now, first thing we need to do is we're gonna run a couple of different web servers pointing to a directory. Let's check some. I'll try to find some example of a HTML file, something better, so we can add, because that one is nothing special. Oh, right, something that's gonna work. So if I go to HTML, I'll just delete this. And I'll just do something like this. First heading, first paragraph. Let's call it Nginx web server. Or you can put anything you want. Doesn't really matter. It's just a sample website. I turned this off, but I didn't make it persistent. This creepy sound. Stupid Windows. Running in Docker. Okie dokie. So now we're gonna set up load balancing. We're gonna set up a reverse proxy and everything at once. So I provided you a configuration file for Nginx in your canvas, but if you don't see it, I can show it, explain it shortly what it does. So I'll just share the screen quickly. This is the configuration file of the SSL Nginx load balancer, aka proxy. So what this does, what we're gonna do actually is we're gonna run 6 different containers of web servers, and we're gonna put them like our backend. So this is gonna be our backend, and in this case, you're gonna assign an upstream, which is gonna be where the servers are gonna be. The incoming connections are gonna go there. And the HTTP upgrade, the connection upgrade, will define your proxying. So we will also define proxy cache. So if you put your volume where the proxy cache will be, if it's an SSD, this is gonna be crazy. Your website is gonna be super fast. So the caching is gonna be in an SSD, and you have turned compression on. These parameters will help you speed up the website. Then the server will listen on port 80 by default. So we can add here also another flag called listen 443 SSL. We can add some additional parameters for this. I have a SSL example here. So you have to use in the proxy pass your name, which we don't have because SSL requires a name of the server, and issuing a certificate needs name. We can't do this with IP address. You can try it with self-signed certificates. And the only thing you need to add is the SSL and the client keys. So I will show you this later. Let's not complicate it for now. So the proxy to be set up, you can paste all this information. These are schemes and attributes that allow the proxy to stale errors, to cache minimum uses. So this is part caching, part proxying, and also load balancer. So these are 3 functionalities in one. So if we put this file in a directory to which we're gonna point with our Docker, let's go back. This is no, one more. So we're gonna create a folder next to the Docker Nginx. We're gonna call it Nginx. Let's call it something that we can distinct. Let's call it Nginx config. So if we check, the folder is here. Pardon. I forget about this all the time. There it is. We create a folder next to the Docker Nginx in your root or wherever you are. We call it Nginx config. So in this file, we put the SSL configuration. So if we go to Nginx config, we create a file called nginxssl.conf. And here you can copy paste the whole thing, because we are not focusing in this case on the configuration of Nginx. You can find this all on their website. It's explained in a terribly big detail, so you can do everything with that little software. Without HTML, please. That's not the way to go. Upstream, that looks better. Everything looks fine. So I can save this. Let me check just a second. Yeah, everything looks okay. Okay, so I'll just save and exit. And now we have the Nginx SSL conf file in this directory. So we have to remember where these are, because we need to map this volume inside the container later when we run them. So this is the serving directory. This is the configuration file directory. Then you can have another directory which will be certificates. You can create it for the time being. Later you can test it if you want. Just to put certificates in there. You don't have to. It's going to work without certificates, but that's how you achieve SSL TLS termination. So the same way, just put Nginx certs, make directory. Nginx certs. I'm mistyping stuff. So if you go to the check, there is the folder, and here you will put all your certificates. So you can try to self-generate, or you can use certbot, which is advisable. You can configure certbot also within Nginx when you run the web servers to initiate a request. I will provide you a file for this, how to do it, so no worries. We're not going to cover it in the tutorial now, but it's just an additional step. The most important is to make the server up and running. So the certificates usually always come later. In any case, you need the folder which you need to map in the container anyways. So these should be put in some safe place, most of them together or in a separate places. If you want to put a caching folder, you just also make directory nginx_cache, and you can map that folder on a SSD or somewhere, and you can have a caching. So that's best practices for administering a website or a web application. So Nginx will serve a website that we tell him to serve. So the way this is going to be done is running a container and assigning it to the network that we created in Docker earlier, the net A. So to do that, you can run a container, docker run -itd, let's say, or just d, doesn't matter, just daemon. We're not going to enter immediately in the container. We can put a flag like this, restart. You can put unless stopped. So the container will restart if it stops. You will have some sort of safeguarding in case something goes down. Let's put a name. let's put a name of this Nginx1 or Docker Nginx1, because this is where it's important. Now I'll show you in the configuration file. Now the IP addressing of these containers is going to be the IP addresses that we assigned in the servers. So your web servers are going to be the ones that we're going to run in the following container. So we're going to run 6 containers, and each of them will have these IP addresses. They will belong to the same net A network that we created with Docker. So you can use DNS entries, and this will be recognizable by the names of the containers in that case. This is how Kubernetes does things, but let's forget about it for a second. So we can use IP addresses for the matter of convenience. So we create upstream called Docker Nginx. So this is important because this is through this upstream you're gonna call your proxy pass. So it means that when you assign proxy pass HTTP through Docker Nginx, all the traffic that goes through your web server is gonna first go through a proxy container, and it's gonna be load balanced between all of these containers using these parameters for load balancing. So connection upgrade using round robin by default. Let's go back to the terminal. So we make a container named Docker Nginx1. So we're gonna have more, and we attach it to a network called net_a, was it? Yeah, net_a, and we give IP to the container. IP equals one of those IPs that we put in the configuration file in the nginx config, nginx_ssl.conf. So here we put IP 172.18.0.3, and now the most important part. Now we have to map a volume using -v root docker nginx. Remember the folder we created where your serving files will be. HTML, this is your serving directory. So this serving directory you map in the container by user share nginx HTML. That's where nginx is running inside the container. This is the default serving directory of the nginx web server. And then you just invoke the container which you want to run, which is the web serving container. Nginx web server. We have another image. Remember Nginx proxy? That's a proxy we're gonna run among the web servers later. So if I press enter, it runs. That's a good sign. Docker ps -a. Well, something's going off. That's not removed container. Let's remove it. It's just gonna create a confusion. Docker remove nginx1. Okay, doesn't require force, easier for me. So the next thing that we're gonna do is we're gonna run more containers. So we need to populate that configuration file scheme. We need to make all of these. So first we run the all 3 that will run 04, 5, 6, 7, and 8. The 2 we are saving for the proxy itself, for the container that's going to use this file to help the load balancer. So what we do is, let me go back to the terminal quickly. So what we do is the same. So you can scroll up and you just run another web server named Docker Nginx2, and you run it with IP4. It's gonna be in the same network, it's gonna be same everything. So it shares the same directory, it serves the same directory. So you see where this is going. We will have 6 containers serving same directory, load balancing between each other, and working as an orchestra in order to serve a lot of users. So if you experience HTTP load, you can scale this up automatically by the HTTP load. So there will be like 10 or 15 more containers running, and you will have real scaling and load balancing. But in our case here, it's not real because we're running everything on one VM. So the container's capacity is limited by the capacity of the VM. If we are running, let's say, these 3 containers on one VM, 3 on another, 3 on another, like we have 3 or 4 VMs, and they're interconnected with each other in this way, then we have a real load balancing. But as long as we are constrained by a single VM, as we're running right now, we just have more or less resilience of failure, because the load balancing comes from the fact that you can add more and more resources. In this case, we can't add more. We can, for example, restrict these 2 containers to run with some RAM memory or some CPU, and then share this equally between each other, and then we will have real load balancing. But the fact is that these containers, by default, they will utilize the whole potential of the host, of the VM. So the container gets all the resources the VM can give it from the hardware. And in this case, we don't really have real load balancing, but we have resilience. So that's what this means. Load balancing needs to be planned in advance, on which hardware you're going to run this, how much resources you have in your underlying fabrics. So we do this the same with the following containers. We need to run 6 of them. So make sure you change the name, Nginx 3. You put number 5, 1805. Then we run more. Nginx 4. Oh, this is a mistake already in use. Need to change the address. 06. Something ran. We're gonna have to stop it. Created, right? So we remove remove docker nginx 4. Okay, let's go back and put 6. Yeah, that's the correct one. Then we put run nginx 5 and 1807. This runs. Then we run one more, the 6th container, which is gonna be 6 1808. Okay, so if we go list all this, everything runs. So we have 6 containers that are serving the same directory, the directory where our files are. So what's next? To use this configuration file we have created before for Nginx, in nginx_config, we need to run one more container that's going to be your proxy. So inside the container, in fact, there is nothing special. I will show you. So if you go inside the container, you can do it like this: docker execute -it interactive mode, and the name of the container. Let's just go in the first one: docker exec docker nginx1 bin bash. Now we are in the container. So you see, we don't have a host name of the container, but the host name is the actual ID of the container. So this is how the containers recognize each other. The ID is a generic way. You can change this, of course. There is a way you can assign host name when you run this. You can add host name, you can add FQDN. There's literally everything possible. But for the sake of simplicity, we're keeping it to IP addresses, so you can see what's going on. Now we are in the container. So the container, if you list it, it has the same structure as Linux, as you can see, because the image on which this container is built upon is Ubuntu. You can build it upon on Windows image, you can build it upon on anything, because as long as the app running inside the container is compatible with the structure, the hierarchical structure of the directories, the binary tree, let's say, of Linux or Windows, it will run. It will not run in between OSs, but it will run on that specific one. So if you put a Linux container, you're not going to run it on Windows, Probably this will be able in the future, but in a Windows container, the Nginx will still run. So you will still have this same procedure on Windows, except the directory will be different. You will have C drive and you have users and documents there and stuff. It's not going to be the Linux directory system. So inside the container, everything is the same. So if we go to etc nginx, you have the same directories like it would be installed on a real computer. So the confd is the file where the directory where the configuration file will be. So here we have default conf. So if you check this, the default.conf is the default Nginx serving. So this is not doing anything except it runs 80 on localhost, and it serves the root directory user share nginx html, and it has some index file, random file. If you don't map directory on your host in the container, the Nginx will serve the files that are inside the container, but these are not good practices. So the container shouldn't have the files that you're serving, because the container can be hijacked, and if it's pushed in a public repository, imagine somebody can just inject something in that somehow. It can exploit a vulnerability in your server, inject a file, and next time you push it to your repository and pull it back, you will have a bot running in your container. So that's how things are done. So if you want to make everything safe, just you can use state scanning of containers and don't put anything inside the container. Everything is on the host. So if I exit the container, we're back in the host. So in the host, we're putting everything as a config here. And when we run the container, it will just replicate everything there. So we are serving a file, but we are not serving a configuration file. So as you see, when we entered in the default.conf inside the container, the configuration file is still old. If we want to put the one that we created, new one, we're gonna have to do that through the proxy, because the proxy is the one who's gonna use that file. These web servers, they don't really need that file. So what's next? Next is we're gonna have to run the proxy container. So docker run in daemon mode, and we'll assign it an IP address. Let's say, no, actually I reserved this, I think, from before. That's why the configuration file starts from 3.18.02. So we'll put the second one to be the proxy. The first one is the gateway, so we can have some order. The same network, net net._a. And now the interesting part, -p 8080. So we expose port 80, allowing HTTP traffic to flow through the reverse proxy. This is the interesting thing. So when you expose port 80, when the traffic comes into the Nginx proxy, this configuration file will see that, and it will do the following lines. So it will allow the traffic to pass, and then it will allow some other stuff like use stale error timeout if you have 504 errors, error codes, background updates, things like that. So it can use cache. So you define this my cache, and my cache is defined as a path. And this path you need to map also, but we're not mapping it for now because we don't really use the cache inside the VM. So caching inside the container or inside the VM is not going to make a big difference, because we don't really know how Ceph in OpenStack is mapping the volumes from the VM. Is it on SSD? Is it on hard disk or something? It doesn't really matter. So you can use the cache as a default place. You can create this directory in your root and you can map it as a volume. Everything that's being cached inside the container will be mapped also inside that directory, as well as certificates and all these things. So all the directories here, you have Nginx certs, Nginx cache, whatever the container does in background, your site is being accessed, these directories will be populated on your host. They will be pushed there and they will be saved on the local volumes. So we just expose port 8080 for the time being. You need to expose 443 if you're using SSL as well. That's the only difference. So we add a name for this container because we need to know what it is, and we're going to call it Nginx proxy. So this is the proxy container. Okay, sorry, just remind me if I forget to switch the screen, because I forget. I apologize for that. Okay, I think it's better like this. So we just add restart. We're gonna have to add some restart policy. Hey, that's not cool. Okay, I'm gonna have to clear screen a bit. I'm gonna start from beginning. Docker run -d, output IP 1802, net A, ports 80 standard, name Nginx proxy, and restart policy. You can put always in case something goes wrong. Somebody's complaining. Can you see the screen now? I started sharing the terminal. Is it possible for you to see? Okay, that's good. That's very good. Thank you. You can put restart always, or you can put restart unless stopped, which is like most default way things are being done. And now you need to map the configuration file root nginx config, and this is mapped directly to the container to etc nginx conf.d. So when you run this container, the configuration file we created, it will go directly to this directory inside the container. And when the Nginx service starts, it will start serving it. It will start pulling information from that configuration file to run the proxy, the cache, the load balancer, everything we did with Nginx. The next thing we do is just invoke the Nginx proxy image, and if we run the container, this should run the Nginx proxy container. So what proxy does is takes all the traffic coming from the public interface on port 80 and 443 TCP and mapping. So it terminates 443 here because these containers didn't know anything about 443 or SSL or anything. Their job is just to serve the files. They're the heavy lifters. That's why we put 6 of them, because we load balance between them in this case. And this is it. Your website is ready to be served. So that's the only thing you need to do. If you create a Docker compose file with this, I will provide you script for this because I don't have it, but you can use this to create also a normal script. I mean, you can try by yourself. I can do it for you, but it's good if you try by yourself because these things are very simple. You just need to understand the mechanism behind the infrastructure part. So in this case, you just have a main entry point, which is going to be this initial container. So everything that's coming on the public interface of the VM, it's going to be redirected from the main interface. Let's call it the public IP because that's where the OpenStack is hosted, and it will go through all this one of these interfaces, which is let's say it's this one. It's a virtual Ethernet. It's the Nginx proxy interface, and this will be actually forwarded through the other containers. So these are all the 6 interfaces that are mapped for the virtual interface for the containers that are running the web server. And that's it. You should have a running website. If I'll try to access this, let me see if it works. It still says forbidden. Maybe it's some sort of caching. I'm gonna try to clear the cache first. Let me check. I'll show you. Clear cache. Well, it gives 403 forbidden because, yeah, sure, no worries, no worries. It just gives a message. It means the server is running. It's not showing that, let me show you. It's not showing that the action, no, it's not permissions per se. I'm not sure it can. Yeah, we'll have a short break. No worries. Right. We can have a short break. No problem. So this is recorded. You can try it. I will provide you example how to do this with Docker Compose, because Docker Compose is something that automates all this process, so you don't have to put all these containers one by one. But I'm just showing you the process how to do this one by one. Next, we can try to install the Docker Compose because it can prove that you can have a problem with that. So what's the deal with this? If I type docker -- version, the version of Docker works with specific versions of Docker Compose. So this is where things getting tricky. So you have to have the right version. So this is, I think, the latest version of Docker. Docker Compose is like this. If you type help, I think it's installed on my computer on the VM. Quite laggy though. Okay, 19 is the latest version. Well, that's cool. Well, Compose obviously refuses to cooperate. Nevertheless, I'll just show you a short introduction how to install it. Let me just find the document while this tries to survive. Yeah. I have also, let me show you this. I will share this with you later. It's a solution, containerized solution, web server and load balancer and reverse proxy with certbot SSL termination. So you can use certbot certificates to automatically renew them after a year or 2 years. Yeah, don't worry. I will explain this through diagram as well. And you will have a more comprehensive overview of what is happening. So I will provide you all these documents as well as something plus. So this is additional. So how to link Nginx and certbot. I have everything ready. I have provided some scripts here for you. So I think this will be just out of the box. You can try all these things if you want to run something in high availability. So before we go to Kubernetes, this is also good to try and know. So the Docker Compose, what it does, the Docker Compose can do all of this the same, but instead of writing everything in a single line like we did now, you just put everything in YAML file and you use Docker Compose up to run everything at once. So to set it up, you can go and check on this website. Let me open this. I provided you links here, so I'll share this on the GitHub for Docker Compose releases. You have which is the latest one or which one works with your version of Docker. So the compatibility matrix is something you need to pay attention to, which version works with which one. This is the website. So you can check this. It's the GitHub repo for Docker Compose. To go back to the file, so you can install it by curl, and you just set permissions to execute locally, and you put it in bin, so user local bin, and that's it. I'll share this document, and we can take a break. Sure. And I think that this is it for today. You can try this for yourself. In the meantime, I will finalize these documents, and I will share them with you because I have this one, and let me show you something more. I managed to collect some stuff for you. Let me check. I think I have also how to deploy Elastic Stack on Docker. Yeah, something like this. So I managed to find the Dockerized version of Elastic Stack. And yeah, there's some best practices how to do this. And there is also a way how to run it with Docker Compose. So it can be just click and run. There is the whole tutorial. It's very short. I will share all this with you. Then I think I have one more, how to run. Okay, let me change the screen to this. Then I will show you how to run the stuff that I just did with Docker Compose. So I'll create this document today and I will share it in Canvas. So I think this is it for today. And I will post the videos so you can rewatch and do by yourself. And please, if there's any questions, just I think it's best if you can message me and Martin on the Discord. Discord is quite nice for chatting. We will close this session here and we can answer you the questions there. So you can send me a private message or in the general chat so everybody can see what problem you have, and let's try if we can solve it. And we're gonna talk a little bit now about the project 2.